The stone beneath Giza does not announce itself. It does not glitter like polished casing blocks once did under the sun, and it does not rise in clean geometry against the desert sky. It waits lower down, beneath the feet, beneath the famous angles, beneath the enormous public face of the pyramids. To stand near the Great Pyramid is to feel pulled upward by the impossible mass of it. But the older and stranger story begins in the opposite direction, in the bedrock, in descending passages, in unfinished chambers, in chemical traces buried in mud, and in the small tools Egypt left behind before history learned how to explain them. The mystery is not that the pyramids were built by magic. The real mystery is more human and, in some ways, more difficult how people using copper, stone, rope, wood, water, surveying skill, and immense organization learned to make stone behave like a controlled machine. At Giza, the landscape itself is part of the engineering. The plateau is not simply a stage on which pyramids were placed, it is the first material. Before the stones climb upward, the builders cut downward, level, test, and adapt. The surface is limestone, but not an even sheet. It has faults, layers, harder beds, softer beds, weathered crusts, and subtle slopes. In places, the living rock is shaped into the pyramid's foundation. In other places, blocks must compensate for the irregular ground. The pyramid does not just sit on the earth, it negotiates with it. That is where the first forbidden feeling of this engineering begins, not in a supernatural secret, but in the strange sense that the monument is only the visible half of a much larger design. What survives above ground is the part meant to be seen. What survives below ground is often the part that makes the visible miracle possible. Before we go deeper, take a moment to like the video and subscribe if this is the kind of history and mystery you enjoy. Because the closer one looks at Egypt's old engineering, the less it resembles a simple story of slaves dragging stones across sand, and the more it becomes a world of workshops, harbours, hidden corridors, ancient survey lines, damaged tools, copper stains, and unfinished spaces where the builder's decisions are still locked into the rock. The title Forbidden Engineering belongs to the atmosphere of the mystery, not to the evidence. Nothing in the mainstream record requires lost electricity, levitation, alien machines, or secret technologies hidden from humanity. Scholars still debate many details, but the real evidence points towards something subtler. Ordinary materials pushed to extraordinary limits by people who understood stone through practice. Their tools were not powerful by modern standards, yet they were used with patience and scale. Their instruments were not digital, yet their alignments could be astonishing. Their machines, when they existed, were not engines of steel, but systems of ramps, sledges, rollers, levers, boats, canals, teams, schedules, and a state capable of turning a landscape into a construction process. And yet the feeling of the forbidden persists because so much of the story is not preserved in obvious form. The pyramids do not come with a complete manual. The builders did not leave behind a full set of architectural drawings explaining every chamber and void. Many tools were recycled, corroded, lost, or broken down. Wood decayed, rope vanished, work camps were buried, harbours dried, branches of the Nile shifted away. Underground spaces were blocked, robbed, altered, or never finished. A tool can disappear from a worker's hand, but still leave a mark in stone. A workshop can vanish, but still leave copper in the sediment. A harbour can dry into desert, but still preserve pollen, silt, and chemical fingerprints. In that sense, Egypt left behind tools that are not always objects. Sometimes the tool is a scar, Sometimes it is a void, sometimes it is a residue. One of the most striking clues comes not from Giza itself, but from a time before the Pyramid Age, when Egypt was not yet the Egypt of Khufu, Khafra, and Menkaura. A small copper alloy object from the pre-dynastic period, long understood as something like an awl, has been reinterpreted as an early metal drill bit used in rotary drilling. If that interpretation is correct, it pushes a key technical habit deep into Egypt's pre-pharaonic past, the habit of making holes through controlled rotation, pressure, abrasion, and tool design. This does not mean pyramid builders had modern drills. It means that by the time monumental stone architecture reached its most famous form, Egyptian craft traditions had already been developing for centuries. The Pyramid Age did not appear from nothing. It inherited hands that knew materials. It inherited workshops that experimented. It inherited a culture in which a tool could be small enough to fit in a palm and still change the way stone, wood, bone, or shell yielded to human intention. This is one of the quieter surprises of ancient engineering. The largest monuments often depend on the smallest technologies. A pyramid may weigh millions of tons, but its story turns on the edge of a copper chisel, the smooth pull of a rope, the grain of a wooden sled, the angle of a lever, the burnish on a stone pounder, the amount of water poured onto sand to reduce friction. The public imagination wants the answer to be a single lost device, one hidden machine that solves everything. The evidence suggests almost the opposite. No single explanation fully accounts for the pyramids because the pyramids were not one problem. They were thousands of problems stacked together. Quarrying is not the same as hauling. Hauling is not the same as lifting. Lifting is not the same as aligning. Aligning is not the same as building chambers that do not collapse under crushing pressure. The genius lies not in one forbidden secret, but in a chain of practical solutions strong enough to survive 4,500 years. Below and around the pyramids, modern science is beginning to read that chain in ways earlier explorers could not. The old image of pyramid research was almost always invasive tunnel, dig, clear, break, enter, expose. Today, some of the most important discoveries come from technologies that try not to touch the monument at all. Muons from cosmic rays pass through stone and reveal differences in density. Ground-penetrating radar sends signals into masonry and soil. Electrical resistivity suggests where buried features may hold air, stone, or disturbed ground. Ultrasound, seismic testing, and image fusion help researchers compare traces that no single method can interpret safely on its own. These tools do not strip the mystery away. In some cases, they deepen it. A corridor appears where no corridor should be visible. An air-filled anomaly lies behind a face of stone. A large void is detected, but its purpose remains uncertain. The evidence becomes clearer, while the meaning remains incomplete. That is why the underground and hidden parts of the pyramid still feel alive. In the Great Pyramid, the descending passage plunges toward a rough subterranean chamber, unfinished and severe, far below the polished geometry that once shone outside. Above the king's chamber, stacked relieving spaces absorb and redirect pressure in a way that appears brutally practical and almost elegant. Recent structural studies suggest that the pyramid responds to vibration differently from the ground around it, and that these spaces may help reduce stress in the chamber below. But here caution matters. It would be too easy to say the builders designed an earthquake-resistant monument in the modern engineering sense. The evidence remains incomplete. What can be said is more grounded and still remarkable. Egyptian builders understood load, weight, pressure, and risk through experience. and they built internal stone arrangements that helped the monument endure forces far beyond daily expectation. Outside the pyramid, the buried evidence spreads wider. The old harbour zones near Giza preserve traces of activity that connect stone monuments to water, transport, metalwork, and supply. Sediment cores from the ancient port landscape show increased copper pollution during the pyramid building period, a chemical shadow of tools, repair, sharpening, and metallurgical work. This is an extraordinary kind of leftover tool, not a chisel in a museum case, not a drill bit held up under light, but a stain in ancient mud. It suggests that the building of pyramids was not just a ceremonial act on a clean desert plateau. It was industrial in the ancient sense, noisy, organized, material-hungry, and dependent on maintenance. Copper had to be obtained, worked, worn down, resharpened, and replaced. Stonecutters did not simply possess tools, they consumed them. The Nile, too, was part of the machinery. Ancient branches of the river once ran much closer to pyramid fields than the modern map suggests, and the now vanished waterways help explain why so many pyramids stand where they do. Boats could carry limestone, granite, provisions, wood, and people through a waterscape engineered by season, canal, harbour, and riverbank. The famous stones didn't move through empty desert alone. They moved through a living logistical system. What survives in the record suggests a civilization that understood the landscape as an instrument. A river branch could be as important as a ramp. A harbour could be as important as a quarry. A causeway could be both sacred road and transport artery. The engineering beneath the pyramids, then, is not only below the stones, it is beneath the modern surface of the desert, hidden in dried channels and buried ports. This first layer of the story changes the way the pyramids should be seen. They are not isolated mountains of stone built by a single trick. They are the frozen summit of a much broader technical world. Under them lies bedrock cut and trusted. Within them lie chambers, stresses, passages, and voids. Around them lie cemeteries, causeways, temples, workshops, and buried anomalies. Beyond them lie quarries, Nile channels, ports, copper sources, scribal records, and the labour of people whose names mostly disappeared. Some left behind tombs, some left behind bones, some left behind nothing more than tool marks on limestone. But in those marks, the lost engineering is still present. And so the mystery begins not with a locked door or a secret chamber, but with a quieter image, a worker long before dawn, holding a tool that will not survive intact, standing on a stone that has already been measured, beside a landscape being transformed piece by piece. Above him, the pyramid does not yet exist. Below him, the ground is already being prepared to carry it. The forbidden part is not that Egypt knew something impossible. It is that Egypt knew so much through methods that were fragile, practical, and rarely written down. The tools were left behind, but not always where we expected to find them. Some are buried beneath the pyramids, some are hidden inside the stones, some are dissolved into the soil, and some remain only as puzzles, waiting in the silence below Giza. Long before the Great Pyramid rises into the Egyptian sky, before Khufu's name is attached to the most famous mass of stone on earth, the Nile Valley is already teaching people how to think in lines, levels, seasons, materials, and repetition. The Pyramid Age is often imagined as a sudden leap, as though one generation woke beneath a desert sun and decided to arrange millions of stones into perfect slopes. But ancient engineering rarely moves like lightning. It moves more like the river itself, gathering sediment, changing course, leaving layers behind. by the time the Old Kingdom builders begin shaping Giza, Egypt has already passed through centuries of experiment. Villages have become towns, chiefs have become kings, ritual spaces have become royal monuments, and simple craft has become specialized production. The pyramids belong to this long inheritance. Their secrets are not only inside their chambers, they begin in the older world that made such chambers imaginable. In pre-dynastic Egypt, before the pharaohs ruled from a unified throne, communities along the Nile are already working with stone, bone, ivory, copper, wood, leather, reeds, clay, and imported materials that travel farther than a local village could see. Objects move through exchange networks. Ideas travel with them. A stone vessel made with astonishing patience, a drilled bead, a polished pallet, a carefully shaped knife, a tomb lined with timber or brick. Each of these small things belongs to the same deep story of control over material. The scale is not yet pyramid scale, but the habit is there. Egyptian craft traditions are learning how to reduce resistance, how to scrape, grind, drill, polish, cut, and fit. How to turn rough matter into a form that carries social meaning. What survives in the record suggests a culture already fascinated by permanence, even before it builds the monuments that would make that fascination world famous. The small copper alloy drill bit from the Badarian or early Naqada world matters because it places rotary tool use deep in that older technical landscape. It is not a dramatic object at first glance. It does not look like a royal treasure. It is the kind of thing that can be overlooked because it appears ordinary, and ordinary tools rarely receive the reverence given to gold masks or carved statues. Yet a tool like this can change the rhythm of a craft. Rotary drilling is not simply poking a hole. It involves controlled spinning motion, pressure, a worked tip, abrasive action, and the knowledge that a material can be persuaded slowly rather than broken violently. Scholars still debate the interpretation of ancient tool marks and the exact range of early drilling technologies, but the broader point remains powerful. Egypt's later monument builders emerged from a world where technical experimentation was already old. This matters because the Pyramid Age is too often treated as an isolated miracle. It was not. The great stone monuments grew from earlier graves, earlier sacred enclosures, earlier experiments with mud brick, timber, and stone. At first, elite burials in Egypt did not rise as smooth-sided pyramids. They were pits, chambers, mounds, mastabas, and increasingly elaborate tomb structures. A mastaba, with its flat top and sloping sides, is already an architectural argument. It says that the dead ruler or elite person is not merely placed in the ground, but housed, marked, protected, and joined to a visible form above. The underground and the surface work together. This pairing becomes one of Egypt's lasting ideas, the hidden chamber below and the visible monument above. Secrecy and display in one structure. The pyramids do not invent that tension. They magnify it until it becomes almost cosmic. Before Giza, Saqqara becomes the great laboratory. The step pyramid of Djoser does not simply appear as a smaller version of later pyramids. It is stranger, older, and in some ways more revealing. Beneath and around it lies a vast complex of courts, dummy buildings, corridors, shafts, galleries, storerooms, and underground spaces that seem to transform royal burial into an entire stone world. Its architect, Imhotep, later becomes legendary. But the building itself is more important than the legend. It shows a society moving from mud brick forms into stone imitation, turning perishable architecture into permanent architecture. Columns imitate bundled reeds. Stone walls echo older materials. Forms that once belonged to temporary or organic construction are translated into limestone. Egypt is not simply building with stone. It is teaching stone to remember older things. The step pyramid also reveals how early pyramid engineering is as much underground as above ground. Its substructure is enormous and complex, a maze of descending passages and chambers cut into bedrock. Thousands of stone vessels, some older than Djoser himself, were found in the underground galleries, suggesting that the king's monument absorbed earlier royal memory into its own design. This is a lesser-known detail, but it matters. The pyramid is not only a tomb or a tower. It is an archive made of stone, a container for objects, rituals, and inherited authority. The underground passages are not accidental service spaces. They are part of the meaning. They create distance between the living world and the royal dead. They protect, confuse, conceal, and dramatize descent. They also force engineers to solve practical problems of cutting, supporting, ventilating, accessing, and sealing spaces beneath a monument whose weight increases as the building grows. Recently, one of the more provocative ideas attached to Djoser's step pyramid has been the hydraulic lift hypothesis, which proposes that water pressure may have helped raise building stones during construction. It is an intriguing possibility because Saqqara's landscape includes ancient water management features, enclosures, channels, and basins that invite big questions about how engineering and hydrology interacted. But this idea must be handled with care. It remains a debated hypothesis, not a settled explanation. No single explanation fully accounts for the construction of the step pyramid, and the evidence for a full hydraulic lifting system is still being assessed. Still, even if the most ambitious version of the hypothesis proves too bold, it usefully reminds us that Egyptian engineering did not happen in isolation from water. The Nile was not only a source of fertility, it was a calendar, a road, a measuring instrument, a labour organiser, and sometimes a force that could be managed. The older world before Giza is also a world of state formation. Engineering at pyramid scale requires more than clever tools. It requires command over time. People must be fed. Work must be scheduled around agricultural cycles. Stone must be quarried, transported, counted, assigned, and placed. Copper tools must be made and repaired. Wood must be obtained in a land where large timber is not endlessly available. Rope must be twisted from fibre. Sledges must be built. Water must be brought to work sites. Specialists must train other specialists. Scribes must record deliveries, teams, and rations. The pyramid is not only a geometric object, it is a social machine made visible in stone. And beneath that social machine lies a quieter technology administration. This is where Egypt's early kingship becomes inseparable from engineering. A local chief can command a grave, a strong ruler can command a large tomb, but a pharaoh, in the Old Kingdom sense, commands a system that reaches from quarry to river, to harbour, to plateau, to temple, to burial chamber. The monument becomes a way of proving that the state itself can organise the world. It aligns the king with cosmic order, but it also proves that fields, boats, workshops, scribes, priests, stonecutters, and haulers can be made to move toward one purpose. The smooth face of a pyramid hides this human complexity. Its simplicity is almost deceptive. The shape is pure, the process is not. The evidence remains incomplete because the most ordinary parts of ancient work are often the first to vanish. A gold ornament may survive because it was valued and buried. A rope survives only under rare conditions. A wooden sled decays unless protected. A copper tool might be melted down, reused, stolen, or corroded beyond recognition. The people who solved daily engineering problems did not always carve their methods into temple walls. They worked by apprenticeship, memory, imitation, and correction. A master mason did not need to write a treatise for every apprentice. He could show how a line should be held, how a surface should be checked, how a tool should strike, when stones sounded wrong, when a block should be rejected. Much of the knowledge that built Egypt lived in bodies before it lived in texts. And so the world before the pyramids is not a primitive prelude. It is the foundation. It is the slow accumulation of gestures and habits that later make Giza possible. The early drill, the polished stone vessel, the mastaba, the underground gallery, the Nile landing, the mud brick enclosure, the survey rope, the copper edge, the scribe's tally, the work gang's rhythm, all belong to the same deep preparation. By the time the pyramid builders arrive at Giza, they are not inventing engineering from nothing. They are inheriting a culture already trained to think downward into the earth and upward toward the sky. That inheritance is what makes the later puzzle so compelling. The tools Egypt left behind are not only scattered artifacts, they are milestones in a long transformation, from small controlled holes in ancient materials to chambers buried beneath mountains of stone. The choice of ground is the first act of pyramid building, and it is easy to underestimate because it leaves no dramatic tool in the hand. A pyramid begins before the first great block is dragged into place. It begins when surveyors, priests, administrators, quarrymen, and royal planners decide that one piece of earth can carry a king into eternity better than another. At Giza, this choice is not random, and it is not only symbolic. The plateau offers height, visibility, stone, dryness, and a commanding position west of the Nile, where the setting sun already carries funerary meaning. But it also offers something more practical and more hidden, a broad limestone foundation that can be cut, levelled, incorporated, and trusted. The builders are not merely looking for a sacred horizon, they are looking for stone that will hold other stone without betraying them. The Giza Plateau is often seen as a desert platform, clean and timeless, but in the Old Kingdom it belongs to a more complicated landscape. The Nile lies closer in ancient channels. Harbours and low-water basins connect the plateau to a living transport system. Flood seasons alter movement, labour, and supply. The desert edge is not an empty boundary, but a zone where river logistics meet stone architecture. This matters because the pyramid field is chosen not only for spiritual geography, but for access. A pyramid must stand in the west, in the realm associated with the dead, but it must also receive limestone, granite, basalt, copper tools, timber, rope, food, beer, water, and thousands of workers. Sacredness alone cannot haul a block. Practical geography must serve cosmic meaning. Recent studies of ancient Nile branches have sharpened this picture. The now vanished Aramat branch, running near many pyramid sites, suggests that pyramid landscapes were once much more connected to water than the modern desert view allows. Earlier work on Nile waterscapes near Giza also supports the idea that channels remained active enough during the reigns of Khufu, Khafra, and Menkaura to help move material into the pyramid zone. What survives in the record suggests a carefully exploited edge environment, not pyramids marooned in sand, but pyramids tied to river arms, ports, causeways, and valley temples. The engineering beneath the pyramids is therefore partly geological and partly hydrological. The builders choose stone underfoot, but they also choose a relationship with water nearby. At the construction level, Bedrock is both blessing and problem. A stable limestone platform can reduce the amount of artificial foundation needed, but natural rock is rarely obedient. It slopes, it cracks, it varies in hardness, it contains fossil beds, joints, and weathered surfaces. The builder must decide what to cut away, what to build over, what to leave as core, and what to mask with casing. Beneath parts of the Great Pyramid, the living rock was not simply covered. It was incorporated into the mass of the monument itself. That means some portion of the pyramid's lower body is not separate quarried block at all, but native plateau shaped into the architectural form. This is a lesser-known detail because the eye wants to read the pyramid as an object placed on top of the earth. In reality, the boundary between monument and ground is blurred. That blurring changes the meaning of precision. When people marvel at pyramid geometry, they often imagine a finished stone shell measured from the outside. But precision has to begin in rougher conditions. A line drawn across uneven bedrock is not the same as a line drawn on a flat table. A level surface must be created or compensated for. A base must be oriented before the rising mass makes correction difficult. Angles must remain consistent across courses. The first mistakes would echo upward, becoming larger and harder to hide. The old Egyptian surveyors, sometimes called rope stretchers in later contexts, worked with simple instruments by modern standards: cords, stakes, sighting tools, plumb lines, leveling methods, and observation of the sky. Yet the results at Giza show that simplicity of tool does not mean simplicity of thought. There is a quiet drama in imagining the beginning of the Great Pyramid not as a crowd hauling stones, but as a nearly empty plateau marked by cords. Before the monument becomes heavy, it is almost weightless, a geometry laid over rock, a royal intention stretched into lines. The builders must decide where north lies, where each side will run, how the base will meet the living stone, and how the internal passages will descend into the body of the plateau. Once those decisions are fixed, the pyramid begins to trap the plane within itself. Every later block obeys the first invisible order. This is one reason ancient engineering can feel forbidden in the dramatic sense. The most important decisions are not always visible in the finished monument. They disappear because they succeed. The sacred dimension deepens the practical one. The west bank of the Nile is not only useful land, it is the side of sunset, burial, transformation, and royal afterlife. The pyramid shape itself may evoke rays of the sun, the primeval mound, or ideas of ascent, though scholars still debate how these meanings developed and overlapped in different periods. What matters here is that Egyptian engineering does not separate the spiritual from the structural. A passage is not only a corridor, a chamber is not only a room, a causeway is not only a road, a foundation is not only a base. These things participate in a world where stone, direction, light, death, kingship, and cosmic order are bound together. The builders do not have to choose between religion and engineering. For them, the greatest engineering exists because the religious purpose demands endurance. This is also why the plateau becomes more than a construction site. It becomes a royal landscape. Khufu's pyramid does not stand alone for long. Khafra's pyramid follows, visually tied to the Sphinx, temples, causeways, quarries, and the natural ridge of the plateau. Menkaur's pyramid completes the famous triad at a smaller scale, but within the same monumental grammar. Around them spread cemeteries for queens, officials, priests, and workers connected to the royal project. The dead gather around the king as administration gathers around power. Beneath the sand and stone, the plateau becomes layered with shafts, mastabas, tombs, passages, walls, and later intrusions. Modern geophysical surveys that detect anomalies in the Western Cemetery or near pyramid faces are not surprising in the broad sense, because this was never an empty place. It was a built and buried environment, used, reused, modified, and sometimes misunderstood. Still, not every anomaly is a secret door, and not every void is a revelation. This distinction is essential. Ground-penetrating radar, electrical resistivity, muon imaging, and other techniques can show differences in density or possible air-filled spaces, but they do not automatically reveal purpose. A buried feature may be a chamber, a trench, a natural cavity, a construction space, a robbed tomb, a later disturbance, or something else entirely. The evidence remains incomplete until multiple methods agree and, in some cases, until careful excavation can confirm what instruments suggest. The modern hunger for hidden cities beneath the pyramids often races far ahead of the data. The real archaeology is slower, more disciplined, and more interesting. It does not need a giant underground metropolis to make the plateau mysterious. The confirmed complexity is already enough. Choosing bedrock also means choosing risk. A monument the size of Khufu's pyramid presses downward with an almost unimaginable load. The builders had no modern stress models, but they had experience with stone failure, cracking, settling, and collapse. Earlier pyramid projects had already shown that large monuments could change plan, deform, or require adaptation. At Giza, the foundation had to resist not only the dead weight of stone, but centuries of weather, minor tremors, temperature changes, human intrusion, and internal stress. Modern research into the Great Pyramid's response to vibrations suggests that its structure behaves differently from the surrounding ground, and that internal features such as the relieving chambers above the king's chamber may help reduce dangerous amplification. It would be too much to claim that Old Kingdom engineers designed in the language of modern earthquake science, but it is not too much to say they understood, in their own way, that heavy stone needed paths for pressure. This is where the sacred bedrock becomes the first hidden tool. It is not handheld, not cast in copper, not displayed in a museum. It is the ground itself, selected, cut, trusted, and absorbed into the monument. Without it, the pyramid is only an ambition. With it, the ambition becomes possible. The plateau gives height to the king, stone to the builders, dryness to the tomb, and access to a river system that feeds the work. It gives the monument a body before the first course is complete. And when the casing stones are stripped, when the harbours dry, when the tools corrode, when the names of most workers vanish, the bedrock remains, still carrying the ancient decision. Under Giza, the pyramid begins as geology. Only later does it become architecture. Once the pyramid rises, it becomes easy to forget that some of its most troubling spaces lie far below the clean slope of its sides. The eye follows the monument upward, toward the vanished point where casing stones once met in brightness. But the builder's path often moves downward first. Under the pyramids, Egypt cuts into the bedrock as if the true monument must pass through the earth before it can climb into the sky. These subterranean chambers and descending corridors are not decorative leftovers. They are among the oldest and most revealing parts of pyramid design, because they preserve decisions made at the beginning, before the superstructure sealed them away. They show planning, experiment, ritual intention, and sometimes hesitation. They also show something more human. Even the most controlled monuments contain unfinished thoughts. The Great Pyramid's descending passage is one of the starkest examples. It begins high in the north face, then angles down through masonry and into the bedrock, driving toward a chamber deep below the base. The movement is physically simple and psychologically powerful. A person entering it leaves sunlight behind, stoops into a narrowing line of stone, and follows a slope that seems to reject the world above. The passage is too plain to feel ceremonial in the later temple sense, yet too deliberate to feel accidental. At its lower end lies the subterranean chamber, rough, irregular, and unfinished, with a floor that appears cut down in places and abandoned in others. It is one of the most puzzling rooms in the most famous pyramid on Earth, not because it is hidden from scholarship, but because it is known and still not fully explained. This unfinished chamber has invited many interpretations. Some scholars see it as an abandoned burial chamber from an earlier phase of the pyramid's plan, before the builders shifted upward to the Queen's chamber and eventually the King's chamber. Others see it as symbolic, perhaps connected to underworld concepts, the primeval Earth, or a ritual geography that does not require polished completion. The evidence remains incomplete because the chamber itself does not state its purpose. It contains roughness where one might expect royal finish, effort where one might expect abandonment, and placement where one might expect significance. That combination is what makes it so difficult. If it were entirely finished, it might fit one story. If it were barely started, it might fit another. Instead, it seems caught between intention and revision. There is a practical lesson in that uncertainty. Pyramid construction was not necessarily a single frozen blueprint executed without change. The monuments look absolute from the outside, but inside they preserve traces of decision-making over time. A chamber might begin as one solution and become another problem. A passage might be cut before later engineering makes it less central. A plan may adapt as the pyramid grows, as royal priorities shift, as structural concerns appear, or as ritual requirements become clearer. No single explanation fully accounts for every internal feature, and the Great Pyramid in particular resists a neat sequence. Its internal arrangement is unusually complex compared with many earlier and later pyramids. It contains downward motion into bedrock, upward motion into the body of the monument, horizontal chambers, narrow shafts, great relieving spaces, and now, thanks to modern scanning, confirmed hidden voids whose purposes remain uncertain. The word chamber can make these spaces sound calmer than they are. A subterranean chamber is not merely a room underground. It is a wound cut into living rock, a space made by removing mass so that another, greater mass can later press above it. Every cut has consequences. The ceiling must hold. The walls must not fracture dangerously. The passage must remain usable long enough for construction, ritual, and sealing. Air, light, debris, and access must be managed. In later imagination, underground rooms become secret places waiting to be opened. For the builders, they were working spaces before they were mysteries. Men had to descend with lamps, tools, measuring lines, baskets, sledges or hauling equipment for debris, and enough organization to keep the work moving in a confined slope of stone. The atmosphere would have been hot, dusty, smoky, and echoing. The calm darkness a visitor senses today is not the darkness of construction. It is the darkness left after the noise has died. Other pyramids show that underground design was not a side issue but a central tradition. Djoser's Step Pyramid at Saqqara contains a vast subterranean complex, with shafts and galleries that turn the royal tomb into an underground palace of sorts. Later pyramids simplify, revise, or redirect that impulse. But they do not abandon the basic idea that the king's afterlife requires hidden architecture below. A pyramid is a visible form over an invisible domain. The public monument announces power. The underground system guards transformation. The burial chamber, storerooms, symbolic passages, portcullis systems, and blocking stones all belong to this deeper logic. Even when the underground design is practical, it participates in a ritual imagination where descent is not only movement through rock, but movement away from ordinary life. The pyramids of the 4th dynasty sharpen this relationship between display and concealment. At Giza, Khufu's pyramid lifts some of its most important chambers into the pyramid's body rather than leaving the burial entirely underground. This is one reason the Great Pyramid feels like a turning point. The king's chamber, built of granite transported from Aswan, sits above the base, protected by massive blocks and topped by relieving chambers. The design moves the royal centre upward while still preserving the descending passage and subterranean chamber below. It is as if two architectural instincts coexist: the old pull into the earth and the new ambition to place sacred space within the stone mountain itself. Scholars still debate exactly why this arrangement was chosen, but the result is a monument whose interior is not a simple tomb plan. It is a sequence of levels, pressures, experiments, and meanings. Menkaur's pyramid, smaller but still formidable, reminds us that hidden interior spaces can continue to surprise, even in monuments long studied. Recent non-destructive surveys on the pyramid's eastern face have identified two air-filled anomalies behind the masonry, raising the possibility of a previously unknown entrance or structural feature. The careful language matters. A possible entrance is not the same as a confirmed secret door, and an air-filled anomaly is not automatically a chamber full of answers. But such findings show that pyramid interiors remain partly unread. Even after centuries of exploration, there are still places where stone hides differences, where instruments detect something the eye cannot see, and where archaeology must move slowly because the monument cannot simply be opened for curiosity's sake. The same is true at Khufu's pyramid with the north face corridor and the larger void detected earlier by the Scan Pyramids project. Modern mography, radar, ultrasound, and combined imaging techniques have confirmed that hidden spaces exist within the monument, but their purpose remains disputed. Some may be structural, relieving pressure above known passages or redistributing loads. Some may relate to construction logistics, allowing access, movement, or staged building processes. Some may have ritual meaning, though that is harder to prove. The evidence does not support wild claims of vast lost cities or supernatural machines beneath the plateau. It does support something more disciplined and more haunting. The pyramid still contains architecture whose function has not been fully recovered. Unfinished spaces are especially valuable because they show process rather than perfection. Finished royal architecture tries to erase labour. Smooth walls hide tool marks, casing hides core masonry, seals hide access, ritual hides logistics, but a rough chamber, a trial passage, a blocked corridor, or an abandoned cut leaves the builder closer to the surface. In these places, one can almost sense the moment before the monument became untouchable. The tool strikes are not always clear, and the sequence is often debated, but the feeling is unmistakable. Here the pyramid is not yet an icon. It is a work site, a changing plan, a technical argument with stone. That is why the subterranean chambers matter so deeply to the larger puzzle. They do not merely sit beneath the pyramids as curiosities. They reveal that Egyptian engineering begins in subtraction before it becomes addition. It cuts voids before it stacks mass. It creates darkness before it creates height. And then, when the building is complete, those voids become the parts most resistant to interpretation. Above ground, the pyramid states its power with overwhelming clarity. Below ground, it speaks in rough floors, sloping passages, blocked ways, pressure paths, unfinished rooms, and air-filled absences. The old builders left tools behind in many forms, but perhaps the most mysterious tool they left was the void itself, space carved from stone, sealed by stone, and still asking what it was meant to do. The descending passage is one of Egypt's most controlled forms of darkness. It is not a natural cave, not a crack widened by chance, and not a tunnel cut wherever the rock allowed. It is measured darkness, angled darkness, darkness with a direction. In the pyramids, movement into the earth is rarely casual. A corridor tilts downward from the north, a shaft drops into bedrock, a chamber withdraws from sunlight, and the person who enters is made to feel the weight of stone not only above the body but around the mind. The engineering is practical, yet it works with the imagination. A passage has to solve access, alignment, and burial security, but it also turns space into experience. In Egypt, descent is never only descent. The north-facing entrance of a pyramid carries its own old logic. In many Old Kingdom pyramids, the main descending passage begins on or near the north side and slopes toward the burial zone. The northern sky mattered to Egyptian royal afterlife beliefs because the circumpolar stars never set. They seemed to turn forever around a fixed region of heaven. Later texts connect the dead king with the imperishable stars, though scholars still debate how fully those ideas shaped every architectural decision in the earliest pyramid designs. Still, the pattern is too persistent to ignore. The passage descends from the north, as if the route into earth and the route toward eternity are bound together. The king is hidden below, but his destiny is imagined above. The architecture holds both directions at once. This tension makes Egyptian tunnels different from ordinary mine shafts or storage passages. They are engineered spaces with symbolic gravity. To cut a descending corridor through masonry and bedrock, the builders must control angle and straightness over a long distance while working inside a narrowing volume. The slope must be usable during construction and burial, then later sealed, blocked, and made difficult to violate. Yet it also must carry ritual meaning, because the king's burial is not merely the disposal of a body, it is the transformation of royal presence into something that continues beyond death. What survives in the record suggests that Egyptians imagined the afterlife through movement crossing, rising, descending, passing gates, joining gods, and becoming effective in another realm. Architecture gives that movement a stone body. The Great Pyramid turns this movement into one of the strangest sequences in ancient building. The descending passage falls into the bedrock, but another route, the ascending passage, rises away from it and leads toward the grand gallery and the upper chambers. This fork in the monument feels almost like a decision preserved in stone. One path continues downward toward the unfinished subterranean chamber. Another climbs upward into the pyramid's interior, toward spaces built with greater finish and heavier structural ambition. No single explanation fully accounts for the shift. It may reflect a change in plan, a layered ritual program, a construction solution, or some combination of all three. Inside the same monument, the architecture offers both burial in the depths and ascent through the stone mountain. The Grand Gallery belongs to the same hidden system of controlled passage. Its corbelled walls rise high above a steep floor, creating a narrow and almost theatrical interior volume. It may have helped move heavy blocking stones. It may have served as a construction corridor. It may have held a ritual significance connected to the king's final journey. The evidence remains incomplete, and the gallery attracts unsupported theories because it looks too strange to be merely a corridor. Yet ancient engineering often creates forms that serve more than one purpose. A space can be practical during construction, protective during sealing, and symbolic after closure. Small shafts deepen the puzzle further. In the King's Chamber and Queen's Chamber of the Great Pyramid, narrow channels run outward from the rooms into the body of the monument. The King's Chamber shaft reached the exterior, while the Queen's Chamber shafts were sealed at their inner ends until modern exploration exposed them. This detail changes the interpretation. If a shaft was sealed from the room, it was probably not designed simply for ordinary ventilation. Some researchers connect these shafts with stellar alignments, perhaps symbolic routes for the king's soul toward regions of the sky. Others caution that exact alignments, dates, and intentions are difficult to prove. The shafts remain elegant uncertainties too deliberate to ignore, too narrow to use, too symbolically suggestive to reduce to plumbing. Modern robotic exploration has made these small passages feel even more mysterious. Small robots have crawled into the Queen's Chamber shafts and encountered blocking stones with copper fittings sometimes described as handles, though their exact function is uncertain. Behind one blocking stone lay further complexity without a simple final answer. These discoveries are a reminder that hidden engineering is not always grand. Sometimes it is a narrow channel barely large enough for a machine, ending at a worked stone placed where no human could comfortably work after construction. The old builders created inaccessible architecture, features meant to exist within the monument rather than to be visited. The pyramid sometimes values sealed intention. The tools needed to create such spaces were not exotic, but the discipline required was severe. A descending passage cut-off angle could compromise alignment. A shaft that wandered unpredictably could lose its symbolic or structural purpose. A chamber placed carelessly could create dangerous stress. Copper chisels, dolerite pounders, stone hammers, wooden mallets, measuring cords, plumb bobs, sighting rods, and abrasive sand all belong to this world. But the most important tool may have been repeated control checking, correcting, smoothing, testing, and measuring again. In a confined passage, errors do not remain private. They are trapped in stone. The accuracy of a hidden shaft is therefore a signature of labour disciplined over distance. Tunnels also belong to security. A royal burial required access before burial and denial after burial. This creates an architectural paradox. The builders must make a route strong enough and clear enough for the most sacred event of the monument's life, then turn that same route into a barrier, blocking stones, portcullis systems, concealed entrances, plugs, and misleading passages all belong to that uneasy logic. Yet tomb robbers eventually entered many pyramids, sometimes through forced tunnels that ignored the intended plan. Security, like symbolism, was never perfect. Still, the underground routes show that Egyptian builders thought carefully about controlled access. A pyramid is not simply closed, it is designed to close. This is why the tunnels and shafts feel so charged. They join engineering to belief, and belief to risk. Their geometry is not only functional, their function is not only mechanical. A descending corridor can be a construction route, a ritual path, a security device, and a symbolic movement into the earth all at once. A narrow shaft can be a technical feature and an imagined road to the sky. A blocked passage can be a defense and a sacred statement. The builders left no full explanation of these choices, and so modern interpretation must stay careful. But careful does not mean dull. The surviving stone is full of intention, even where the exact intention has slipped away. Beneath the pyramids, the human body is forced into the scale of the monument. The visitor bends, descends, climbs, waits, and feels the air change. That physical experience may preserve something of what the builders understood: stone can control movement, and movement can control meaning. The pyramids are famous because they rise, but their mystery endures because they also draw downward and inward. In their tunnels, Egypt turns engineering into passage, passage into ritual, and ritual into sealed geometry. The tools that made their spaces may be gone, but the paths remain, still guiding the imagination through darkness measured 4,000 years ago. Stone looks still only because human lives are short. To the pyramid builders, limestone and granite were not motionless substances, but materials with moods, weaknesses, grains, seams, and memories of pressure. A block could split the wrong way. A roof beam could crack. A chamber could become a trap if weight was not persuaded to move around it. The desert plateau seemed dry and eternal. Yet even here water had shaped the rock before the builders arrived, and would continue to trouble the monuments after they were sealed. Beneath the pyramids, the great engineering puzzle is not only how stone was lifted, but how stone was made to endure once lifted. The real test begins after the last worker leaves, when the monument must carry itself without mercy. Every pyramid is an argument with gravity. The larger the monument, the more severe the argument becomes. A small tomb can rely on walls and roof stones. A giant pyramid must manage a mountain of compressive force. Millions of blocks press downward and inward. The weight seeks paths through the masonry, through chambers, through corridors, through the natural foundation. If that pressure is badly handled, the monument may crack, settle, distort, or collapse in ways that are difficult to repair once construction continues above. Ancient Egyptian builders did not speak in the language of modern structural engineering, but they clearly learned from stone. They saw what happened when walls leaned, when roofs failed, when earlier monuments changed shape, when a passage roof needed support, when a chamber demanded protection. Their science was not written as equations. It was stored in experience. The Great Pyramid's king's chamber is the clearest place to feel this pressure made visible. The chamber itself is built of granite, a stone harder and stronger than the surrounding limestone and transported from far to the south. But even granite has limits, especially when roofed by enormous beams beneath the mass of the pyramid. Above the chamber, the builders created a stack of spaces often called relieving chambers. These are not ceremonial rooms in the usual sense. They are rougher, hidden, and functional in appearance, placed above the king's chamber like a stone device for redirecting danger. At the top, angled blocks form a kind of protective roof, helping move weight away from the flat granite beams below. The arrangement is one of the great quiet achievements of pyramid engineering, a hidden structure built not to be seen, but to keep another structure from dying. Recent studies of vibration and structural response have given this old arrangement renewed interest. Measurements taken inside and around the Great Pyramid suggest that the monument does not respond to ground motion in exactly the same way as the surrounding terrain, and that internal features such as the pressure-relieving spaces may reduce the amplification of stress around the king's chamber. This does not prove that Khufu's engineers deliberately designed an earthquake-resistant pyramid in the modern sense. That would go beyond the evidence. But it does suggest that choices made for load management may have helped the pyramid survive, forces its builders could not fully predict. In other words, the monument's endurance may come from practical wisdom that later appears almost scientific when measured with modern instruments. Pressure also operates below the visible architecture. The foundation must carry the pyramid without shifting unevenly. The Giza limestone plateau helped, but it was not a perfect slab. Natural bedrock contains layers, joints, weathered zones, and variations in strength. Where the builders could use living rock, they did. Where they had to level or fill, they had to do so with care. Uneven settlement would have been dangerous, especially for a monument whose base required extraordinary alignment. A pyramid tolerates some roughness in its core, but it cannot tolerate uncontrolled failure in its foundation. What survives in the record suggests that the builders were willing to incorporate the plateau into the monument precisely because they trusted selected rock more than an entirely artificial base. The ground itself became a structural tool. Water complicates the picture because the pyramids now seem to belong to dry desert. But their ancient setting was never simply dry. Seasonal Nile floods, canals, harbours, and groundwater patterns shaped the working environment. The water that made transport possible could also make foundations, quarries, and low-lying areas unstable or difficult. Around Giza, ancient harbour basins and Nile branches supported the movement of materials. Yet these watery landscapes left deposits, sediments, and long-term traces beneath what later became dry ground. The builders had to understand where water helped and where it threatened. They needed access to the river, but they also needed royal monuments high enough, dry enough, and stable enough to outlast the living waters below. The Sphinx and nearby cuttings reveal another side of water's relationship with stone erosion. The Giza limestone is not uniform, and some layers weather more easily than others. Wind, salt, moisture, rare but intense rainfall, and long exposure all alter the rock. Scholars still debate the precise history and relative importance of different erosion processes, especially around the Sphinx enclosure. But no serious interpretation can ignore the fact that stone is vulnerable over time. The builders chose a plateau that could support monuments, yet the same natural rock could be carved, weathered, undercut, and repaired. Egypt's monuments survive not because stone is invincible, but because stone fails slowly enough for endurance to be mistaken for permanence. Inside pyramids, water is less visible but still important. Moisture can move through cracks, affect salts, damage surfaces, and alter underground spaces. In tombs and chambers, changes in humidity caused by visitors, openings, restoration, or environmental shifts can create conservation problems. The ancient builders sealed spaces partly for ritual and security, but sealing also created microenvironments, some stable, some not. A blocked chamber may preserve air, dust, and surfaces differently from an open corridor. A buried passage may remain protected for centuries, then begin changing quickly once exposed. This is why modern exploration must be cautious. Opening a hidden space is not only an act of discovery, it changes the thing discovered. Stress is not always dramatic. Sometimes it appears as a hairline crack, a shifted block, a ceiling beam under tension, or a subtle difference in vibration. The Great Pyramid contains cracks in some of its granite beams, showing that even the hidden relieving system did not create a world without strain. It created a world where strain could be managed well enough. That distinction is crucial. Ancient engineering does not need perfection to be extraordinary. It needs success across time. A cracked beam that remains stable for thousands of years tells a more realistic story than an untouched miracle. It tells of builders working near the limits of their materials, making choices that reduce danger without eliminating it. Other pyramids show what happens when those limits are tested differently. The bent pyramid at Dusha famously changes angle partway up, likely reflecting structural concerns during construction. The Meidum Pyramid suffered catastrophic collapse or outer casing failure, though its exact construction history remains debated. These monuments are not embarrassments in the story of pyramid building. They are lessons. They show that the Old Kingdom was not following a flawless secret recipe. Builders experimented, learned, adjusted, and sometimes faced consequences. By the time Giza's great monuments were planned, Egyptian engineers had inherited not only successes, but warnings written in stone. The hidden stress beneath the pyramids is therefore not a single mystery but a constant negotiation. Weight presses downward, rock pushes back, water shapes the setting, moisture enters cracks, time tests every shortcut. The builders respond with foundations, core masonry, chamber placement, granite beams, relieving spaces, careful siting, and a willingness to let the natural plateau do part of the work. They do not defeat nature. They recruit it where possible and resist it where necessary. That is the deeper engineering beneath the pyramids, not a forbidden machine, but a disciplined conversation with pressure, water, and stone. And in that conversation, the tools Egypt left behind become harder to define. A copper chisel is a tool, a drill bit is a tool, but so is a relieving chamber, so is a levelled bedrock platform, so is a harbour placed close enough to serve construction but far enough from the sacred high ground. So is the decision to lift the burial chamber into the pyramid's body and protect it with stacked spaces no visitor was meant to admire. The builders understood that the most important engineering might vanish from view if it worked properly. The monument would stand, and the hidden struggle would disappear into silence. Beneath the pyramids, that silence is still carrying the weight. The builders' most important work may have happened before the pyramid looked like anything at all, long before the sides rose in clean triangular planes, before the casing stones flashed in the sun, before the burial chambers were sealed and the causeways received their last processions. The project existed as lines, counts, marks, orders, and sequences. A monument that appears simple from a distance becomes almost impossibly complicated at the level of planning. Every stone has to arrive at the right place in something like the right order. Every tool has to be sharpened, replaced, or repaired. Every team has to know what kind of work it is doing that day. The pyramid is not only a pile of blocks, it is a schedule made physical. This invisible planning begins with measurement. The base must be established on the ground with extraordinary care, because the rising mass will magnify early mistakes. Surveyors stretch chords, sight along lines, mark corners, check levels, and return to the same measurements again and again. The later Egyptian title connected with rope-stretching hints at the ritual and technical prestige of this act. Though scholars still debate exactly how Old Kingdom surveyors achieved the most precise alignments, they may have used stellar observations, shadow methods, water levelling, sighting instruments, or combinations of practical techniques refined by tradition. What matters is that the geometry of the pyramid begins as an invisible grid imposed on rough land. A cord pulled tight across limestone can become the ancestor of a wall that will outlive kingdoms. Precision also depends on knowing the landscape in 3 dimensions. The builders do not merely mark a square on flat ground. They must understand where the plateau rises, where it dips, where bedrock can be cut, where natural rock can be included in the core, and where artificial levelling is required. They must plan internal passages before the pyramid mass traps them. The descending passage cannot be improvised after millions of stones are in place. The chamber positions, approach routes, blocking systems, and structural protections belong to early decisions. In that sense, the pyramid is planned downward and upward at the same time. The visible monument grows above the earth, but its hidden logic is already being fixed below. Then comes the larger question of supply. To build at pyramid scale, Egypt has to turn distance into routine. Limestone from nearby quarries can feed the core. Fine casing limestone from Tura must cross the river. Granite from Aswan must travel hundreds of kilometers from the south. Basalt, timber, copper, gypsum, food, beer, water, fibers, and people must move through networks that are not accidental. The Nile makes this possible, but not automatically. Boats must be loaded, docks maintained, channels used at the right seasons, and cargo tracked. The now dry river branches and harbour landscapes near pyramid fields show that water transport was part of the construction machine. The pyramid rises in stone, but behind it is a choreography of boats. The Diary of Mera gives a rare glimpse into that choreography. It does not reveal a grand secret machine, and that is exactly why it is so valuable. It records ordinary movement teams transporting limestone from Tura toward Akhet Khufu, the horizon of Khufu, through a controlled administrative world of officials, routes, and deliveries. This kind of evidence pulls the pyramid out of fantasy and back into logistics. The Great Pyramid becomes not less astonishing, but more astonishing in a human way. It was built by a society that could coordinate river journeys, quarry work, accounting, provisioning, and placement, with enough consistency to make the extraordinary feel routine. Copper traces in the ancient port sediments add another kind of planning to the picture. The tools were not merely used, they were consumed. Copper chisels and blades dull quickly against stone, especially hard stone. They have to be resharpened, reforged, replaced, and transported through the same supply system that feeds the workers. The increase in copper pollution around Giza's harbour zone during the pyramid building period suggests intense metalworking activity tied to construction. This is one of the more surprising details because it means Egypt left behind the shadow of its tools in mud. The actual tool may be gone, melted, recycled, or corroded beyond recognition, but its chemical ghost remains in the ground, quietly recording an industrial rhythm around the royal monument. Arsenical copper tools from the Giza workers' settlements deepen this world of practical skill. These were not magical instruments, and they were not as hard as iron or steel, but they were part of a real technical system. Alloy composition, casting, hammering, annealing, sharpening, and repair all mattered. A copper tool could cut limestone when used correctly with abrasion and repeated effort, but it was not a simple solution to every problem. Harder stones required pounding, grinding, drilling with abrasives, and immense patience. The evidence remains incomplete because many tools were reused and because workshops rarely survive in perfect condition. Still, what survives suggests a construction culture in which metal workers and stone workers depended on each other constantly. The older rotary drill tradition belongs here as well. A small early drill bit from long before the Pyramid Age reminds us that Egyptian engineering is not only about brute force. Rotation, abrasion, pressure, and control all belong to the deep craft background of the Nile Valley. By the Old Kingdom, craftspeople could drill beads, hollow stone vessels, shape hard materials, and create astonishingly precise forms through techniques that seem slow to modernize, but powerful when multiplied by labor and time. The pyramid builders inherited this mindset. They understood that resistance could be worn down. A stone did not have to be conquered in one strike. It could be persuaded through repeated contact. Planning also means organizing people without reducing them to a faceless mass. The old image of pyramid building as pure forced misery has been heavily revised by archaeology. The workers' settlements at Giza suggest organized labor communities with food supply, administration, medical care, craft specialization, and team identities. This does not mean the work was easy or romantic. It was physically brutal by modern standards, but it was not chaos. It's a structured labor serving a royal and religious project at the center of the state. Work gangs likely had names, supervisors, and divisions of responsibility: bakers, brewers, butchers, toolmakers, haulers, sailors, quarrymen, masons, scribes, and priests all belong to the same vast undertaking. The pyramid is a social landscape compressed into architecture. There is a lesser-known kind of intelligence in the sequencing of construction. Blocks do not simply arrive and wait forever. Space on the plateau is limited. Ramps, roads, working surfaces, storage zones, and access routes change as the pyramid grows. A route useful at one height may become useless later. A chamber must be roofed before the mass above becomes too great. A passage must remain accessible until it is sealed. Temporary structures may leave little trace, especially if dismantled, buried, or reused. Scholars still debate ramp systems and lifting methods because the evidence is partial and because more than one method may have been used at different stages. The desire for one perfect answer may be misleading. A pyramid this large may have required changing solutions as its shape changed. The builder's invisible planning therefore lives in absences: the missing ramps, the vanished ropes, the decayed sledges, the reused copper, the erased chalk marks, the lost work orders, the sealed chambers, the dried canals, all point to a technical world that was once obvious to the people inside it. They did not need to explain every step to the future. They needed the work to continue tomorrow morning. Their knowledge was practical, shared, corrected, and repeated until it became almost invisible. That invisibility is what makes the finished pyramid seem impossible. We see the final stone mountain, but not the thousands of ordinary systems that made it inevitable. And yet the systems have not disappeared completely. They survive in a papyrus from the Red Sea, in copper-stained sediment near a harbour, in tool marks on limestone, in the orientation of the base, in the buried geometry of passages, in the workers' town, in the quarries, and in the very fact that the pyramid still stands. The builder's greatest tool was not one object, it was coordination. It was the ability to make stonecutters, sailors, scribes, surveyors, priests, cooks, metal workers, and labour crews act as parts of one long process. Under the pyramids lies bedrock, but beneath the bedrock of the monument lies planning invisible, disciplined, and almost completely consumed by the success it created. Inside the Great Pyramid, the underground puzzle begins with the descent that seems almost too severe for the monument around it. Outside, the pyramid is geometry made visible, a vast triangular certainty rising from the plateau. Inside, the first ancient route does not rise at all. It cuts downward from the north, narrow and steep, passing through the masonry and then into the bedrock beneath the pyramid's base. The transition matters. At first, the passage belongs to the built pyramid, to blocks placed by human hands. Then it enters the living rock of Giza itself, as if the monument is returning to the material from which it was born. The deeper one follows it, the less the Great Pyramid feels like a pure object above the ground. It becomes a structure with roots, a stone mountain joined to a carved underworld. The subterranean chamber waits at the bottom of that descent with none of the finish people expect from royal architecture. It is rough, uneven, and strangely unresolved. Its walls and floor preserve the feel of a work interrupted or redirected. There is a pit-like cut in the floor, irregular surfaces, and a horizontal passage extending beyond, adding to the sense that the space was not brought to a final polished state. This is not a hidden room in the romantic sense, filled with treasure and sealed messages. It is more unsettling than that. It is a known room whose meaning remains uncertain. It sits beneath the most mathematically famous pyramid in the world, yet it refuses to behave like a clean answer. For a long time, one common interpretation has been that the subterranean chamber represents an abandoned original burial chamber. In this view, Khufu's builders may have begun with a more traditional plan, placing the royal burial deep beneath the monument, then altered the design as construction developed, eventually moving the king's chamber upward into the pyramid's body. The ascending passage, grand gallery, queen's chamber, and king's chamber then become evidence of a changing plan. A sequence of architectural decisions that grew more ambitious as the monument rose. This interpretation has the strength of simplicity, because unfinished work often suggests abandonment. But simplicity can be dangerous in a monument that repeatedly refuses to be simple. The evidence remains incomplete, and the chamber's roughness does not by itself prove why it was left that way. Another possibility is that the chamber's unfinished condition had some symbolic or ritual value, though this is harder to demonstrate. Egyptian ideas about the underworld, primeval waters, the earth, rebirth, and the king's transformation were complex, and they developed across time. A rough chamber carved into bedrock might have carried meanings that a polished granite room could not. It might have represented the deep earth, the hidden realm, or an older stage in a ritual journey. But here the evidence becomes slippery. It is tempting to turn every rough surface into a symbol, just as it is tempting to turn every symbol into a construction accident. Neither extreme is safe. What survives in the record suggests that the subterranean chamber belongs to a real architectural plan, but whether that plan was abandoned, transformed, symbolic, practical, or some mixture of these remains debated. The chamber is also part of a larger internal contradiction. The Great Pyramid has one of the most elaborate interior arrangements of any Egyptian pyramid. Many pyramids have relatively straightforward descending passages and burial chambers, but Khufu's monument combines downward and upward systems in a way that still unsettles interpretation. From the descending passage, an ascending passage rises into the pyramid, leading ultimately toward the grand gallery in the upper chambers. The result feels like a fork in the monument's logic. One route goes into the earth, another climbs into the artificial mountain. If the lower chamber was abandoned, why preserve access to it at all if it was meaningful? Why leave it rough if the upper chambers were the final plan? What role did the lower system retain? No single explanation fully accounts for all these choices. The physical difficulty of creating the descending passage should not be overlooked. Cutting a long, straight, angled corridor through bedrock requires control and discipline. The builders had to remove stone from a confined space while preserving alignment and slope. Debris had to be hauled out against the incline. Lighting had to be maintained. Air would have been poor. Tool marks, correction. And the gradual subtraction of rock would have shaped the workday in ways very different from placing blocks above ground. The descending passage is often treated as an architectural line on a plan, but in reality it was a cramped and punishing worksite. Its accuracy is a clue to the builder's skill, and its existence shows that the pyramid was conceived not merely as a stack of masonry, but as a union of masonry and excavation. The underground puzzle deepens because the Great Pyramid's interior also reveals a concern with pressure that reaches far beyond the lower passage. The king's chamber, high above the subterranean level, is protected by the famous relieving chambers, a stack of hidden spaces that redirect the load of the pyramid away from the flat granite beams below. These chambers are rough, functional, and inaccessible in the original completed monument. They were not made to impress visitors. They were made to solve a problem. Their existence shows that Khufu's builders understood that hidden voids could serve structural purposes. This matters when thinking about other voids, known and unknown, within the pyramid. A void is not automatically a room, a shrine, or a secret archive. It may be a pressure solution, a construction feature, a consequence of building sequence, or something else entirely. Modern scanning has made this caution more important, not less. The scan pyramid's discoveries, including the north face corridor and the larger internal void detected above the Grand Gallery region, have shown that significant hidden spaces still exist in the Great Pyramid. The north face corridor, confirmed through multiple non-destructive techniques, lies behind the chevron area on the north face. Its discovery is extraordinary because it proves that the pyramid can still contain designed spaces unknown to earlier explorers. Yet even here, the purpose is uncertain. It may help relieve pressure over the original entrance area. It may relate to construction logistics. It may connect to a larger hidden system, though that remains unproven. The evidence points to architecture, but not yet to a complete story. The larger void, often popularly called the Big Void, is even more provocative because of its scale and position. Detected through muon imaging, it suggests a substantial low-density area inside the pyramid, above or near the Grand Gallery zone. But muon data can reveal the presence of a density anomaly more easily than it can reveal function. It does not show wall decoration, ritual use, or contents. It does not identify whether the space is one chamber, a series of spaces, a construction corridor, a relieving feature, or a different kind of architectural arrangement. Unsupported claims rush into this silence because the imagination dislikes restraint. But the responsible mystery is stronger than the exaggerated one. There really is a large hidden feature in the Great Pyramid, and we really do not yet know exactly what it is. This is where Giza's underground puzzle becomes a lesson in how ancient and modern tools meet. The Old Kingdom builders used copper, stone, rope, wood, sight lines, and labour organisation to create spaces that modern researchers now read with muons, radar, ultrasound, and image fusion. One set of tools made the voids, another set detects them, but neither set automatically explains them. A modern instrument can show that something is there, yet still leave the ancient intention concealed. That gap between detection and meaning is where the pyramid's mystery now lives. The old explorers wanted entrances. Modern scientists often find anomalies. Both can be thrilling, but neither is the same as understanding. The subterranean chamber remains central because it is the opposite kind of mystery from the hidden voids. It is not inaccessible. It can be entered, measured, photographed, and described. Its roughness is visible. Its incompletion is not speculation. And still, after all that access, certainty slips away. The chamber reminds us that archaeology is not only limited by what is hidden, it is also limited by what survives without explanation. A room can be open and still be silent. A passage can be clear and still refuse to say why it was cut. The Great Pyramid's lower system is therefore not a solved footnote beneath the better-known upper chambers. It is one of the monument's oldest unresolved arguments. In the end, the underground puzzle of Giza is powerful because it reverses the usual way people look at the Great Pyramid. The monument is famous for its height, but its most human traces may lie in its depths, the cramped labour of excavation, the change of plan or meaning, the rough chamber left unresolved, the hidden spaces designed for pressure or purpose, and the modern instrument still trying to read stone without harming it. Above ground, Khufu's pyramid seems to declare that something has been mastered. Below ground, it admits that mastery was never simple. It was trial, adjustment, pressure, uncertainty, and silence. The deeper passage does not lead to a final answer. It leads to the place where the pyramid is still unfinished in the mind. The Great Pyramid does not stand alone. Even when the imagination isolates it, its mystery is easier to sell as a single monument against an empty desert. But Giza was never empty, and Khufu's pyramid was never a solitary machine. Around it lies a larger engineered landscape of causeways, temples, quarries, tombs, harbour zones, walls, ramps or roadways now mostly vanished, and older natural stone reshaped into sacred architecture. To understand what lies beneath the pyramids, the eye has to widen from the underground chamber to the plateau itself. Giza is not only a place where pyramids were built, it is a place where bedrock, river, ritual, labour, and royal memory were connected into one immense system, and some of that system remains hidden not inside the pyramids, but between them. The Sphinx is the most famous reminder that the plateau itself could become architecture. Unlike the pyramids, which were assembled block by block, the Sphinx was carved largely from the living limestone of Giza. It is not simply placed in the landscape, it is released from it. Its body emerges from bedrock left standing inside a quarried enclosure, while blocks cut from around it may have been used in nearby temple construction. That relationship is easy to miss because the Sphinx is now seen as a statue, a mysterious guardian with a damaged face and a body stretched low against the earth. But in engineering terms, it is also a negative monument. It exists because stone was removed. The builders did not only pile stone upward, they carved sacred form downward and outward from the plateau. This makes the Sphinx enclosure one of the most revealing places at Giza. Its walls expose layers of limestone with different strengths and weathering patterns. Some beds are harder, others softer, and the body of the Sphinx itself has suffered because the stone is not uniform. The monument's long history of erosion, burial, exposure, repair, and reburial shows that Giza's stone was always both resource and risk. Scholars still debate details of the Sphinx's original date, exact builder, and some aspects of its early meaning, though the mainstream view places it in the Old Kingdom, most commonly in relation to Khafra's complex. The evidence remains incomplete in places, but the essential point is clear: the same plateau that carried pyramids also supplied sculptural, architectural, and symbolic forms directly from bedrock. The Sphinx also changes how one reads the pyramid complexes around it. Khafra's pyramid, Valley Temple, Causeway, Sphinx Temple, and the Sphinx itself appear to belong to a carefully organized sacred landscape. The causeway does more than connect buildings. It guides movement between the low valley world near the river and the high desert world of the pyramid. A valley temple receives processions, materials, offerings, and ritual attention. A causeway rises westward. A mortuary temple stands against the pyramid. The pyramid itself dominates the horizon. In this arrangement, engineering is choreography. Stone structures control how bodies move, how priests approach, how offerings travel, and how the king's presence is maintained after death. The hidden part is not always a tunnel. Sometimes it is the logic of movement beneath the visible plan. Causeways are especially important because they sit between practical and sacred meanings. In later ruins, they may appear as ceremonial roads, but during construction and use they also shaped access across difficult terrain. They could link valley installations to pyramid temples, cross slopes, frame sight lines, and possibly assist in moving materials or organizing traffic, though the exact construction logistics varied and are still debated. A causeway is not as dramatic as a chamber or void, yet it may preserve the memory of how a pyramid complex functioned as a system. The river brings goods close, the valley temple receives them, the causeway draws movement upward, the pyramid complex transforms movement into ritual. No single feature explains Giza because Giza is an arrangement, not a collection of isolated monuments. The quarries around Giza belong to this arrangement as well. Some of the stone used in the pyramids came from nearby quarry zones, meaning the act of extracting material also reshaped the plateau. The landscape was lowered, cut, squared, and scarred. In some places, quarrying may have helped define the spaces later occupied by temples, roads, or monuments. This is one of the lesser-known transformations of Giza. The builders were not merely bringing stone to a sacred place. They were making the sacred place by removing stone from it. The plateau became both source and setting. A quarry face could become a wall. A leftover ridge could become a statue. A cut surface could become part of a route. The difference between natural landscape and built landscape blurred with every block removed. Beyond the royal monuments, the cemeteries spread across the plateau like an administrative map of the afterlife. Officials, priests, royal relatives, and people connected to the pyramid system were buried in mastabas and shafts around the Great Pyramids. These tombs are not random additions, they form neighborhoods of status, loyalty, and proximity to the king. The living administration of Egypt leaves its echo in the dead city of Giza. Beneath the sand are shafts, burial chambers, offering chapels, sealed spaces, robbers' tunnels, and later disturbances. Modern geophysical discoveries in areas such as the Western Cemetery, including shallow geometric features and deeper anomalies detected by radar and electrical methods, fit this broader pattern of a crowded underground landscape. But caution remains essential. An anomaly may be a tomb, a shaft, a disturbed zone, a construction feature, or something not yet understood. Instruments can suggest hidden structure. They cannot always name it. This is where the modern myth of vast hidden realms beneath Giza often grows beyond the evidence. The plateau genuinely contains buried architecture, unknown features, voids, shafts, tombs, and unresolved anomalies. That is true, and it is fascinating enough. But viral claims of enormous hidden cities beneath the pyramids have not been confirmed by mainstream archaeology. They take the real strangeness of the plateau and inflate it into certainty. The responsible view is more measured and more durable. Giza was an intensely engineered and reused landscape, and there are still buried features worth investigating carefully. The mystery is not diminished by refusing exaggeration. It becomes stronger because it remains attached to stone, soil, instruments, and evidence. The Sphinx, in this wider setting, becomes less a lone guardian and more a key to the plateau's method. It shows that Egyptian builders understood the ground itself as workable sacred material. They could carve into it, build on it, align across it, quarry from it, bury within it, and connect it to the river below. The pyramid's engineering does not stop at the pyramid's edge. It extends through causeways, temples, quarries, harbour basins, cemeteries, and bedrock forms. The plateau is a machine of memory, but not a machine of gears. It works through direction, height, stone, access, concealment, and repetition. And so, after the darkness of the Great Pyramid's lower passages, the story returns to open space with a different understanding. The desert surface is not simply the top of the buried world, it is another layer of design. Under the sand, old routes and structures continue. In the limestone, quarry scars and carved forms remain. Around the pyramids, tombs and anomalies wait in the ground. Near the Sphinx, the living rock still carries the marks of extraction, weather, repair, and royal imagination. Giza's greatest hidden engineering may not be one chamber beneath one monument, but the way an entire plateau was turned into a single royal landscape. The pyramids rise from it, but they do not exhaust it. The stone below, the roads between, and the buried spaces around them keep the wider puzzle alive. Royal burial in Egypt was never only an ending, it was an engineering event, a religious transformation, a security problem, and a political performance sealed into stone. By the time a pyramid was ready to receive its king, years of quarrying, hauling, measuring, cutting, and building had already turned the landscape into a machine of sacred preparation. But the most delicate moment came near the end, when the monument had to change from worksite to closed world. Passages that had carried workers, tools, lamps, ropes, blocking stones, and ritual equipment now had to become barriers. Chambers that had been accessible had to become unreachable. A route designed for entry had to be converted into a route of denial. In that final transformation, the pyramids reveal one of their deepest contradictions. They were built to proclaim royal power forever, yet their most important spaces were designed to disappear. The burial chamber was not a display room in the modern museum sense. It was the hidden centre of royal continuity, a place where the king's body, name, rituals, and cosmic destiny were protected from ordinary disturbance. Egyptian belief gave the dead king an ongoing role in the divine order, and the tomb was part of that role. It held presence, it anchored offerings, it connected the royal body to rituals performed outside, in temples and chapels, where priests maintained the relationship between the living kingdom and the transformed ruler. The pyramid's visible mass announced that relationship to the world, but the chamber itself withdrew from it. The more sacred the centre became, the more carefully it had to be concealed. Security, however, was never a simple matter of hiding a door. The builders had to plan for the fact that the burial required access first. Heavy objects had to enter, ritual actions had to be completed, the king's remains had to be placed inside with the proper equipment and protection. Only after that could the tomb be sealed. This meant the architecture had to work in stages. A passage remained open while the monument was prepared. Blocking stones waited for the correct moment. Granite plugs, portcullis slabs, sealed corridors, and concealed entrances were not afterthoughts. They were tools of transition, changing a living construction route into a dead king's protected path. A pyramid security system was therefore not one device but a sequence. The Great Pyramid shows this logic in especially dramatic form. Its ascending passage was sealed by massive granite plugs that slid or were placed into position, blocking the route upward toward the Grand Gallery and the upper chambers. These plugs were not subtle in their physicality. They were dense, stubborn, and difficult to remove. Yet even they did not make the pyramid invulnerable. Ancient intruders eventually bypassed intended routes by forcing their own tunnel through the masonry. This is one of the uncomfortable truths of pyramid engineering. The builders could delay violation, confuse it, and make it dangerous, but they could not guarantee eternal protection. No single explanation fully accounts for the mixture of confidence and vulnerability inside these monuments. They were built for forever by people who knew that human greed was patient. This does not make the security systems failures. It makes them realistic. A sealed royal tomb had to resist not only physical entry but knowledge itself. The fewer people who understood the final arrangement, the safer the burial might be. Yet pyramid construction required many workers, supervisors, and specialists. Complete secrecy was impossible at the scale of Giza. The solution was not pure secrecy, but controlled knowledge. Different teams may have known different parts of the structure. Blocking systems could conceal the final route. Ritual closure could mark the transformation of a chamber from accessible to forbidden. What survives in the record suggests that secrecy in Egypt was often architectural rather than absolute. The stone did not merely hide things, it reorganized who could know them. The idea of forbidden engineering belongs most naturally here. Not forbidden because it came from some lost supernatural science, but forbidden because the finished monument created spaces that ordinary people were not meant to enter again. The engineering was designed to become inaccessible. Hidden shafts, sealed chambers, rough relieving spaces, blocked corridors, and concealed voids were not failures of communication with the future. They were part of the monument's success in its own world. Modern curiosity often treats every sealed space as a message addressed to us. Ancient Egypt may have intended almost the opposite. Some spaces were meant to work silently, not to be interpreted by strangers thousands of years later. The tools of burial security were often simple, but their placement made them powerful. A granite plug is not mechanically complex, yet inside a narrow passage it becomes a formidable obstacle. A portcullis slab is only a stone lowered into a slot, but once in place it changes the meaning of the corridor. A hidden entrance does not need to be invisible forever. It only needs to defeat expectation long enough for the sacred closure to hold. In some pyramids, corridors turn, descend, rise, narrow, or end in blocking systems that make movement difficult and uncertain. These features remind us that ancient engineering did not always aim at speed or convenience. Sometimes it aimed at resistance. There is also a symbolic side to this resistance. The king's burial was protected not only from thieves, but from disorder. To violate the tomb was not merely to steal objects, it was to disrupt a carefully maintained relationship between body, name, offerings, monument, and cosmos. Later Egyptian texts and practices show deep concern for the integrity of the dead and the preservation of memory. Though the evidence for every Old Kingdom belief remains incomplete, still. The architecture itself expresses the concern clearly. The pyramid hides the body beneath overwhelming order. Its sides are straight, its base is measured, its passages are controlled, its chamber is sealed against decay, theft, and time. Egypt answers with geometry. And yet tomb robbery became one of the great realities of Egyptian history. Even the most sacred spaces were not immune. Economic pressure, political instability, insider knowledge, and the sheer value of burial goods all threatened royal tombs. In later periods, priests and officials sometimes moved royal mummies from original tombs into hidden caches to protect them, creating another layer of secrecy and displacement in Egypt's funerary landscape. The Pyramid Age already contains the seed of that problem. To bury a king with wealth and sacred equipment beneath a visible monument is to create both a shrine and a target. The pyramid says, "Here is power." Security must then whisper, But not here, not easily, not by the path you expect. This tension may help explain why Egyptian royal burial eventually moves away from pyramids toward more hidden tombs in places like the Valley of the Kings. The change was not caused by one factor alone, and scholars still debate the balance of religious, political, economic, and security reasons. But the problem is visible. A pyramid is magnificent precisely because it is visible, and dangerous for the same reason. The monument's public form guarantees memory, while its hidden chamber invites intrusion. Later kings sought different answers, burying themselves in concealed valleys, while separating tomb and mortuary temple in new ways. The pyramid's engineering had solved one vision of eternity, but eternity kept changing its demands. At Giza, the sealed and violated spaces leave modern researchers with a difficult inheritance. A robbed chamber may preserve architecture but lose contents. A forced tunnel may reveal access but damage original context. A blocked passage may still hide information, but opening it risks changing or harming what remains. Non-destructive scanning now offers a way to detect hidden features without immediately violating them, which is why mammography, radar, ultrasound, and resistivity matter so much. These modern tools respect, at least in principle, the ancient fact of closure. They let researchers ask what stone conceals before deciding whether stone should be disturbed. Burial, security, and secrecy therefore sit at the heart of the pyramid puzzle. They explain why so much was built to be unseen, why voids might be structural or sacred, why passages might be practical and symbolic at once, and why modern claims must be handled carefully. The pyramids were never meant to be fully legible. Their most important act was concealment under pressure, concealment under ritual, concealment under millions of tons of stone. The tools Egypt left behind include the chisel and drill, but also the plug, the seal, the hidden path, and the deliberate refusal of access. Beneath the pyramids, engineering becomes a kind of silence, and that silence was not accidental. It was designed. The deeper the pyramid story goes, the more crowded the explanations become. Stone chambers and buried anomalies do not remain empty for long in the human imagination. They attract theories, and the theories often reveal as much about the modern world as they do about ancient Egypt. Some explanations are careful, slow, and built from evidence that can be tested. Others rush toward the dramatic answer before the stone has finished speaking. Beneath the pyramids, the real challenge is not simply finding hidden spaces. It is learning how to think about them without turning every void into a revelation and every uncertainty into a secret. A void inside or beneath a pyramid can mean many things. It may be a chamber, it may be a corridor, it may be a construction gap, it may be a relieving space placed to shift pressure, it may be a natural cavity in the bedrock, it may be a robber's tunnel, a later disturbance, a collapsed zone, a sealed shaft, or a feature whose purpose changed during construction. This is why modern non-destructive surveys are powerful but not final. Mammography can reveal differences in density. Radar can suggest boundaries and cavities. Electrical resistivity can show contrasts in the subsurface. Ultrasound can identify internal features and discontinuities, but none of these techniques automatically translates a signal into a story. An instrument can say that stone behaves differently here. It cannot always say why ancient people made it that way. The North Face corridor in the Great Pyramid shows how careful interpretation works at its best. For years, the chevron area above the original entrance drew attention because of its unusual arrangement and possible hidden function. Modern scanning eventually confirmed a corridor-like void behind the north face. That confirmation did not require breaking open the pyramid in a reckless search for treasure. It came through overlapping methods, each reading the monument in a different way. The discovery is exciting precisely because it is real, but even after confirmation, its purpose remains debated. It may relieve pressure above the entrance. It may be connected to a construction process. It may protect or conceal another feature. The evidence remains incomplete, and the responsible answer is not less mysterious because it refuses to pretend otherwise. The larger void detected within Khufu's pyramid presents an even more difficult problem. Its scale makes it tempting to imagine a hidden chamber, a royal secret, or an unknown passageway waiting behind stone. Yet the detection of a large low-density area does not reveal contents, decoration, ritual purpose, or access. It may not be a single room in the way the imagination wants. It could be a series of spaces or a structural feature related to load management. It could have been part of construction. It could be something not yet described well by existing categories. Scholars still debate the interpretation because the data are both extraordinary and limited. The pyramid gives a signal, not a confession. Menkaur's pyramid adds another layer to this problem. The air-filled anomalies behind its eastern face may indicate a previously unknown entrance or internal feature, and that possibility is genuinely important. A new entrance would change how researchers understand the pyramid's plan and perhaps the sequence of access and sealing. But the language has to remain conditional. Possible does not mean proven. Reasonable does not mean certain. Ancient monuments often produce features that resemble patterns before they are understood. A cavity behind masonry may have been intentional, accidental, structural, or later. Until further testing or carefully controlled exploration clarifies the matter, the anomaly remains a clue, not a conclusion. The same caution applies beyond the pyramids themselves. In the cemeteries and subsurface features around Giza, ground-penetrating radar and electrical resistivity have detected a shallow L-shaped structure and a deeper anomaly in the western cemetery near the Great Pyramid. These findings are compelling because they suggest that even well-known areas of Giza still contain buried architecture or disturbances that have not been fully explained. Yet the function remains unknown. It may be a tomb structure, a shaft, a passage, a filled trench, or something else. The point is not to drain the mystery away. The point is to protect it from being ruined by certainty too early. Archaeology often begins with a shape, then spends years asking what kind of human action created it. This is where disputed popular theories enter the story. Claims of a vast hidden city beneath the pyramids have circulated widely, especially when fragments of real geophysical research are blended with speculation. These stories are powerful because they borrow the authority of scientific instruments, while escaping the restraint of scientific interpretation. They take genuine features, voids, anomalies, unknown spaces, buried structures, and inflate them into a complete underground civilization. But mainstream Egyptology has not confirmed such a hidden city under Giza. The evidence does not support the grand claim. There are real buried features, there are real voids, there are real unresolved questions. That is very different from a mapped subterranean metropolis. The distinction matters because ancient Egypt's actual engineering is already astonishing. It does not need to be rescued by fantasy. The builders quarried and moved stone at enormous scale. They shaped bedrock into foundations and monuments. They cut passages with difficult alignments. They managed load above chambers. They built harbours and causeways into a changing Nile landscape. They left traces of copperwork in sediments and tools in settlements. They created sealed spaces that modern instruments can still detect after thousands of years. To replace this with vague talk of forbidden machines or lost superscience is not an upgrade. It is a loss of detail. It makes the ancient builders less visible, not more. Still, fringe ideas persist because the pyramids sit in a rare emotional space. They are familiar and unknowable at the same time. Millions of people recognize their shape, but even specialists cannot explain every internal feature with final confidence. That gap invites projection. Some imagine lost technologies because they underestimate ancient labor organization. Others imagine hidden archives because they want the pyramid to be a message for the modern world. Others distrust ordinary tools because ordinary tools seem too small beside millions of tons of stone. But the mismatch is misleading. A copper chisel is small, a state is not. A rope is simple. Thousands of coordinated ropes are not. A sled is basic. A transport system tied to river branches, harbours, work gangs, scribes, and quarries is anything but basic. The hydraulic lift hypothesis proposed for Djoser's step pyramid belongs in a more serious but still unsettled category. It is not the same as a fantasy claim. It is an attempt to interpret landscape features, water management, and construction possibilities in a new way. The idea that hydraulic force may have assisted building is intriguing, especially because water clearly mattered in Egyptian logistics and landscape planning, but it remains debated, and it should not be presented as the accepted solution to pyramid construction. Its value, even if revised or rejected, is that it pushes researchers to think more carefully about water, engineering, and ancient experimentation. Good hypotheses can be useful without being final. A similar balance is needed for earthquake resilience studies. Modern measurements suggest that the Great Pyramid structure, including its internal pressure-relieving chambers, may have helped it endure ground motion in ways that can be analysed today. But that does not mean the builders designed it with modern seismic theory. The safer and stronger conclusion is that their practical solutions for load and stability created resilience. Ancient engineers did not need to know equations of vibration to recognize that heavy stone above a chamber required relief. They did not need modern terminology to build with caution born from experience. The competing explanations below the pyramids therefore form a spectrum. At one end are confirmed features with uncertain function. At another are hypotheses that may or may not survive further testing. Beyond that lie unsupported claims that turn uncertainty into spectacle. The task is not to remove mystery, but to rank it honestly. Some mysteries are grounded in stone, some are grounded in instruments, some are grounded in gaps between evidence and interpretation. Others are grounded mainly in desire. The pyramids can hold the first three, they do not need the fourth. Beneath Giza, the most durable mystery is not that Egypt hid an impossible technology. It is that Egypt built so much with technologies that were possible, human, and still hard to reconstruct in full. The voids remain, the anomalies remain, the unfinished chamber remains, the copper traces remain, the river branches lie buried in old sediment, the tools are scattered, corroded, or gone. Between careful explanation and unsupported invention, the pyramids continue to occupy the more interesting middle ground, understood enough to prove ancient skill, incomplete enough to keep asking for patience. The most misleading thing about the pyramids may be the word simple. Copper tools sound simple, wooden sledges sound simple, rope, mud, water, stone pounders, ramps, levers, and human teams sound simple. The mistake is to confuse simple materials with simple systems. Ancient Egypt did not need steel cranes or diesel engines to create a powerful technology. It needed repeatable methods, trained hands, predictable supply. and enough administrative force to make thousands of small actions converge on one vast result. The tools were modest, the organization was not. Beneath the pyramids lies an engineering world where the machine is not a single device, but the entire society in motion. To cut limestone, Egyptian workers used copper chisels, stone hammers, wooden mallets, dolerite pounders, abrasive sand, and patient repetition. Copper is soft compared with iron, and this has often led to doubt from people imagining construction as a contest between one tool and one block. But ancient stoneworking was not usually so direct. Limestone can be worked with copper tools, especially when the work is divided into quarrying, dressing, levering, trimming, and finishing. Harder stones such as granite require different treatment, pounding with harder stone balls, sawing or drilling with abrasives, grinding, polishing, and immense time. The evidence remains incomplete for every exact sequence, but surviving tool marks, unfinished objects, quarry traces, and experimental archaeology all point in the same direction. The tools worked because the methods were adapted to the material. The old drill bit from pre-dynastic Egypt belongs to this deeper history of adaptation. A rotating tool does not defeat material by force alone. It uses motion, pressure, and abrasion to turn a tiny point of contact into progress. That principle appears again and again in ancient craft. Stone vessels with hollowed interiors, beads drilled through hard material, wooden fittings, shell ornaments, and later architectural details all depend on the idea that careful repeated motion can make a resistant substance yield. The pyramid builders inherited this craft logic. They lived in a world where patience was a technology. A modern viewer sees slowness and thinks weakness. An ancient craftsperson sees slowness multiplied by teams, days, seasons, and royal command. Alignment required a different kind of tool, the disciplined line. A rope stretched between stakes is not impressive until one realizes what it can become. With cords, plumb lines, sighting rods, levels, and astronomical observation, builders could establish orientation, straightness, verticality, and proportion. Scholars still debate the exact method used to align the Great Pyramid so closely to the cardinal directions, but the likely answers do not require impossible instruments. They require careful sky-watching, repeated observation, and skilled correction. The Egyptians lived under a sky less obscured by modern light and more integrated into ritual and timekeeping. Stars, shadows, and horizons were not abstractions. They were part of the working environment. Moving stone is where the ancient tool system becomes most misunderstood. The popular imagination often searches for one lifting device that explains the whole pyramid, but moving a block from quarry to final position is a chain of different problems. It must be cut free. It must be shaped enough to move. It must be dragged or carried to a loading area. It may need to travel by sled, by road, by boat, by canal, by harbour, by causeway, and then up onto the growing monument. Each stage has its own tools and risks. A sledge is not enough without a prepared surface. A boat is not enough without water deep enough to float it. A ramp is not enough without teams, maintenance, traction, and space. No single explanation fully accounts for all movement because movement itself changed at every stage. Water helped in more ways than one. It floated cargo along the Nile and its branches. It supported harbours and basins near pyramid fields. It may have helped prepare surfaces for dragging sledges, as experiments and tomb imagery suggest that wetting sand can reduce friction under certain conditions. It organized the labor calendar because flood seasons changed agricultural work and transport possibilities. The pyramid was built from stone, but its construction was inseparable from water. The Aramat branch and the Khufu-era waterscape remind us that the desert view is deceptive. The blocks did not cross only dry emptiness. They moved through a landscape where river engineering and natural channels did much of the heavy logistical work. Lifting remains debated because the material traces of ramps and temporary systems are fragmentary. Straight ramps, zigzag ramps, spiral ramps, internal ramps, levering systems, and combinations of methods have all been proposed. Some ideas work better for lower courses, others for higher levels, and some may have been used only in particular contexts. It is possible that the ancient builders did not rely on one elegant answer. They may have used changing systems as the pyramid grew, dismantling or burying temporary structures as they became obsolete. The desire for a single hidden solution may say more about modern expectations than ancient practice. A flexible construction culture could solve different heights with different methods. This flexibility is visible in tool maintenance as much as in lifting. Copper tools wore down quickly. That was not a fatal weakness if workshops stood close enough to repair and recast them. The copper traces found in the ancient Giza harbour sediment suggest a zone of intense metal use and maintenance during the pyramid building period. This chemical evidence is easy to overlook, yet it may be one of the most intimate records of the work. Every dull edge, every resharpened blade, every repaired implement belonged to the daily rhythm of construction. The pyramid consumed copper the way it consumed bread, beer, rope, and human effort. A tool was not a permanent possession, it was part of a cycle. The workers themselves were also tools in the broadest ancient sense, though not in the dehumanizing way the old stereotypes suggest. They were skilled participants in a coordinated system. Quarrymen knew the sound of stone. Haulers knew rhythm and strain. Boat crews knew currents, loading and timing. Surveyors knew lines and stars. Metalworkers knew heat and alloy. Scribes knew counts, rations, and delivery schedules. Bakers and brewers kept bodies working. Overseers coordinated teams. Priests tied construction to royal meaning. The pyramid is the result of all these roles fitting together. It is less like a machine built from gears and more like a living organism made of specialized functions. One lesser known but essential point is that ancient engineering often depended on standardization. Blocks did not all need to be identical, especially in the core, but recurring sizes, repeated procedures, team divisions, and predictable tasks made large-scale work possible. A mason who understands the expected finish of a casing block does not need a new invention every day. A hauling crew that knows its rope positions and rhythm can repeat the action thousands of times. A scribe who tracks deliveries can keep material moving before shortage becomes crisis. Repetition turns human labor into infrastructure. The pyramid's apparent stillness hides a construction process built from rhythm. The absence of machines in the modern sense does not mean the absence of engineering intelligence. It means the intelligence was distributed. Some of it was in tools, some was in hands, some was in administrative records, some was in river timing, some was in the way stone blocks were shaped to fit their position, some was in the decision to use bedrock where possible and quarried masonry where necessary. Some was in hidden spaces above chambers that redirected pressure. The builders did not need one forbidden device because they had a culture capable of making many ordinary devices work together at extraordinary scale. That is why the tools Egypt left behind can feel almost disappointing at first, then more impressive the longer one looks. A copper blade does not look equal to a pyramid. A rope does not look equal to 1,000,000 stones. A wooden sledge does not look equal to a mountain. But history is rarely built by objects in isolation. It is built by systems that make small objects powerful through repetition and coordination. The ancient Egyptians did not leave behind a lost engine under the pyramids. They left something harder to imitate, evidence of a society that could turn simple tools into monumental consequences. The true machine was not hidden in one chamber. It was spread across the river, the quarry, the workshop, the work gang, the scribal office, the ramp, and the stone itself. The pyramid did not vanish from Egypt all at once. It faded, changed, returned in altered forms, and gradually lost its place as the supreme answer to royal eternity. This is one of the most important clues in the story of hidden engineering, because a civilization does not abandon a monument type as powerful as the pyramid simply because it forgets how to build. The change is slower and more interesting. The meaning of kingship shifts. The economy strains and reorganizes. Religious ideas develop. Security problems become harder to ignore. Stone, labor, landscape, and memory begin to demand different solutions. The pyramid had once joined visibility and concealment in a single form. Over time, that balance became unstable. In the Old Kingdom, the pyramid was the perfect public statement of royal power. It rose above the desert edge, visible from far away, tied to the sun, the west, the royal cult, the temple, the causeway, and the carefully ordered cemetery. The king's body was hidden, but the monument was not. That contrast was the point. The pyramid told the kingdom where power had gone and where offering should continue. It made the dead king permanent in the landscape. Yet the same visibility that made the pyramid effective also made it vulnerable. A royal pyramid could never truly hide. It could conceal its chamber, block its passages, and confuse intruders. But it also announced that something worth protecting lay inside. This tension did not destroy pyramid building immediately. It shaped it. Later pyramids became smaller, less massive, and often more dependent on mud brick cores, stone casing, and complex substructures. The Middle Kingdom kings still built pyramids, but their monuments often reveal a different mood. They are still royal, still sacred, still tied to the old tradition, yet they stand in a world where the unquestioned grandeur of the Fourth Dynasty is no longer easy to reproduce. Some Middle Kingdom pyramids contain elaborate underground systems with hidden chambers, multiple corridors, portcullises, and architectural traps. If the Old Kingdom pyramid often overwhelms with mass, some later pyramids overwhelm with concealment. The engineering energy moves downward into security and complexity beneath a less imposing surface. This is a crucial transformation. The pyramid's exterior may shrink, but the underground puzzle can grow more intricate. Builders experiment with hidden access, false passages, blocked routes, and burial chambers placed far from the obvious axis. The monument still says pyramid from outside, but inside it behaves almost like a defensive labyrinth. This suggests that royal engineers understood the problem of tomb violation very well. They did not simply repeat older designs out of habit. They adapted. The evidence remains incomplete for exactly how each design was planned and how effective each system proved. But the trend is clear enough as time passes. Secrecy becomes more elaborate, and the visible monument becomes less able to guarantee safety by sheer sacred authority. Eventually, the New Kingdom takes the logic even further. Royal burial moves away from pyramids and into hidden rock-cut tombs in the Valley of the Kings. The mortuary temple is separated from the burial place. The king's public cult can continue in one location, while the body is hidden in another. This is one of the great architectural reversals in Egyptian history. Instead of placing the royal tomb beneath a visible mountain of stone, Egypt cuts the tomb into a natural mountain and tries to hide the entrance in a desert valley. The pyramid form does not disappear completely from Egyptian symbolism, and small pyramid-like markers survive in some contexts. But the Grand Royal Pyramid as the main burial solution gives way to a different underground strategy. The Valley of the Kings is often described as a place of secrecy, but even there secrecy was imperfect. Tombs were robbed, entrances were found. Political instability and economic pressure opened what theology tried to close. Later priests moved royal mummies into caches for protection, creating one of the strangest afterlives of Egypt's burial engineering kings removed from the monuments built for them, hidden again by later generations who inherited the failure of earlier security. This should not be read as incompetence. It is a reminder that no architecture can fully defeat time, need, and human knowledge. A tomb is designed against intrusion, but it is built by people, guarded by people, remembered by people, and eventually betrayed or forgotten by people. Looking back from the Valley of the Kings to Giza, the pyramids become part of a long experiment in how to protect sacred presence. The earlier solutions placed chambers below mastabas and pyramids, joining hidden burial to visible monument. The Great Pyramids magnified the monument until the superstructure became almost cosmic. Later, pyramids complicated the underground routes, trying to outwit intrusion. New Kingdom tombs separated visibility from burial, hiding the body while allowing the cult to remain public elsewhere. Each stage solves one problem and creates another. A visible monument preserves memory but attracts thieves. A hidden tomb protects the body but risks losing public identity. A complex passage delays intrusion but may still be mapped by those who built it. No single explanation fully accounts for the shifts because they involve religion, politics, economy, technology, and fear working together. The tools change with the tomb ideas. Pyramid builders at Giza needed massive transport systems, quarry operations, levelling works, casing blocks, harbours, and labour organisation at extraordinary scale. Valley tomb builders needed different skills cutting long corridors into limestone cliffs, carving decorated chambers, managing ventilation and debris inside mountain passages, concealing entrances, and painting religious texts across walls. The engineering focus moves from stacking stone into the sky to cutting a sacred book into the earth. The old downward impulse remains, but the visible form changes. Egypt never abandons the underworld. It changes the way it reaches it. This shift also helps explain why some pyramid knowledge became harder for later ages to reconstruct. When a building tradition fades, its practical details fade with it. The methods of quarrying, ramping, hauling, casing, aligning, and sealing on the scale of Giza may have remained partly in memory, partly in archives, partly in workshop habits, and partly in institutions that changed over time. Later Egyptians looked back at the pyramids with reverence, but not necessarily with complete technical continuity. By the time Greek and Roman visitors stood before them, the pyramids were already ancient beyond easy explanation. Their original worksite logic had vanished under myth, tourism, priestly storytelling, and sand. That is one reason modern observers attempted to imagine forbidden knowledge. The pyramids seem to appear in history with overwhelming force, then recede into smaller and different forms. But the pattern does not require lost supernatural technology. It fits the changing conditions of a state. A monument type that is possible under one political, economic, and religious arrangement may become impractical or undesirable under another. The Old Kingdom pyramid was not just an engineering object. It was the product of a particular form of centralized kingship, labor mobilization, landscape control, and solar royal ideology. When those conditions changed, the architecture changed with them. The abandonment of the pyramid as Egypt's dominant royal tomb therefore reveals something profound about ancient engineering. Engineering is never only about what can be built. It is also about what a society chooses to build, what it can afford, what it fears, what it believes, and what failures it remembers. The pyramids were not stopped because they were simple solved objects. They were left behind because Egyptian answers to death, security, power, and eternity continued to evolve. Under their stones remain the earlier solutions' blocked passages, hidden chambers, unfinished rooms, pressure systems, sacred foundations, and the bold confidence of kings who believed visibility could protect memory. Later, Egypt learned to distrust visibility. It went deeper, darker, and more hidden. And in that movement away from the pyramid, the old monuments became even more mysterious, not because their engineering was forbidden, but because the world that made them possible had passed below the horizon. Modern science approaches the pyramids with a strange kind of humility. Earlier explorers often tried to reach the unknown by force, cutting tunnels, clearing shafts, breaking through blocks, and prying open sealed spaces in the hope that the next chamber would explain the monument. Today, some of the most revealing tools are designed to do almost the opposite. They listen before they touch. They measure differences in density, resistance, vibration, moisture, and hidden air. They read stone as a body with internal conditions. This shift matters because the pyramids are no longer treated only as ancient objects to be opened, but as fragile structures whose secrets must be approached carefully. The modern tool is not always a pick. Sometimes it is a particle from space passing silently through limestone. Muon radiography is one of the most elegant examples. Cosmic rays strike the upper atmosphere and create muons, tiny particles that pass through stone more easily than many other particles can. By measuring how many muons arrive from different directions, scientists can detect variations in density inside a large structure. More muons passing through a region may suggest an empty or less dense space. Fewer may suggest denser stone. In a pyramid, this becomes a way of seeing without entering. It does not produce a simple photograph like an open doorway. It produces a map of probability, a shadow of density, a clue. Yet that clue can be powerful enough to reveal a hidden corridor or void that remained invisible for thousands of years. The Scan Pyramids project made this new era visible to the public. The discovery of the North Face corridor in Khufu's pyramid showed how several non-destructive techniques could converge on the same hidden feature. Tomography suggested an anomaly. Radar and ultrasound added other forms of evidence. Later imaging confirmed that behind the chevron stones on the north face lay a corridor-like space. This was not mythology, not a rumour, not a treasure hunter's fantasy. It was genuine architectural feature, detected by instruments and then carefully verified. But the discovery also showed the limits of modern certainty. Finding a corridor does not automatically explain why it exists. It may relate to pressure relief above the original entrance, construction sequencing, or another feature still unknown. The instrument reveals presence. Interpretation must still move slowly. The larger void detected within the Great Pyramid is even more tantalizing. It is substantial enough to matter, and yet it remains difficult to define. Is it one continuous space, several connected spaces, a construction feature, a relieving zone, or something not yet recognized? The evidence remains incomplete because tomography can identify density differences but not easily reveal shape, finish, access, or meaning in the way a human eye might hope. This is one of the great frustrations of modern pyramid science. The better the instruments become, the more carefully their results must be interpreted. A strong signal is not the same as a full explanation. The void is real as an anomaly, but its story is still unfinished. Menkaur's pyramid has recently joined this world of careful uncertainty. Surveys using radar, ultrasound, and electrical methods identified 2 air-filled anomalies behind the eastern face, raising the possibility of a previously unknown entrance or internal feature. That possibility is exciting because Menkaur's pyramid is smaller and often less publicly discussed than Khufu's, yet it may still contain structural surprises. But again, caution is the strongest form of respect. A possible entrance is not yet a confirmed entrance. An air-filled anomaly is not automatically a chamber with ritual purpose. The modern instruments have opened a question, not closed it. The pyramid has not yielded a secret so much as presented a new silence in measurable form. Khafra's pyramid is also being approached with cosmic particles. The SIDEP muon radiography project aims to scan the monument from multiple angles, using detectors positioned in and around the pyramid to search for unknown structures or density variations. This is significant because Khafra's pyramid, despite its famous profile and relationship to the Sphinx landscape, has not surrendered the same level of internal complexity in the public imagination as Khufu's. It may prove simpler. It may not. The important point is that modern science no longer assumes that a monument is fully known because its main chamber has been entered. Stone can preserve unknown arrangements, construction features, or natural complications that older exploration missed. Beyond the pyramids themselves, geophysical survey has widened the hidden map of Egypt's necropolises. At Saqqara, researchers use seismic refraction, ground-penetrating radar, and electrical resistivity to detect buried tombs, walls, voids, and subsurface features without immediately digging. In the Western Cemetery at Giza, radar and resistivity have revealed geometric structures and deeper anomalies that may represent buried architecture or disturbed ground. These tools are especially important in crowded archaeological landscapes where excavation can destroy context as easily as reveal it. The ground beneath Egyptian cemeteries is layered with construction, reuse, robbery, collapse, later burial, and natural change. Modern science helps choose where to look and where not to cut. The science of sediment has been just as revealing as the science of stone. Ancient harbour zones near Giza preserve chemical and environmental traces of pyramid construction. Copper pollution in sediment cores points to intense metallurgical activity during the rains associated with the Great Pyramids. This is not the kind of evidence that appears in adventure stories, but it may be more important than a dramatic hidden door. It shows the pyramid project as a working industrial landscape, with tools being made, repaired, worn down, and used at scale. The metal did not vanish completely. It sank into mud as a chemical memory. Modern analysis retrieves that memory grain by grain. Environmental research has also redrawn the ancient map. Studies of vanished Nile branches, including the Ahramat branch and older waterscapes near Khufu's harbour, show that pyramid fields were once connected to river systems much more closely than today's dry desert suggests. This changes the old question of how stones moved. The answer is not only ramps or sledges, it is also channels, harbours, flood regimes, boats, and a landscape that has since transformed beyond recognition. Modern satellite imagery, coring, geomorphology, and pollen studies make visible the missing water roads of ancient Egypt. The engineering under the pyramids includes rivers that are no longer rivers. Even structural vibration studies now contribute to the picture. By measuring how the Great Pyramid responds to movement at different points, researchers can explore how its mass, chambers, and foundation behave under stress. The pressure-relieving chambers above the king's chamber, long understood as structural features, can now be examined in relation to the monument's broader stability. Again, the finding should not be inflated into a claim that Old Kingdom builders practiced modern earthquake engineering, but it does show that their choices created a structure with complex and durable behavior. The pyramid survives not as a static lump of stone, but as a body that responds to forces. What modern science reveals, then, is not a single grand solution. It reveals a more intricate problem. The pyramids are not empty symbols, nor are they sealed vaults of impossible technology. They are engineered landscapes whose evidence exists at many scales: cosmic particles, hidden air pockets, chemical traces, buried riverbeds, tool marks, structural vibrations, and unfinished chambers. Each method sees one layer, none sees everything. That is why the mystery remains alive in a disciplined way. The more carefully researchers study the pyramids, the less they look like simple monuments, and the more they appear as systems of stone, water, labour, stress, ritual, and time. Modern tools do not end the ancient puzzle. They make the puzzle sharper, and they return attention to the oldest truth beneath Giza. What the builders made visible was only part of what they built. The unfinished mystery beneath the pyramids is not a single locked chamber waiting for one final opening. It is a layered absence, made from missing tools, sealed corridors, damaged contexts, vanished waterways, unfinished rooms, and ancient decisions that worked so well they disappeared into the monument. After following the bedrock, the shafts, the voids, the copper traces, the river branches, the harbours, the pressure chambers, the cemeteries, and the modern instruments that now pass through stone without breaking it, the puzzle becomes less like a riddle with one answer, and more like a buried system whose parts were never meant to survive equally. Some parts were built to be seen from miles away. Some were built to be hidden forever. Some were temporary and vanished as soon as the pyramid was complete. Some were never finished at all, together. They leave a mystery that is more difficult than fantasy because it belongs to real human work. The phrase tools Egypt left behind begins with objects, but it does not end there. A drill bit from before the pharaohs, copper blades from Old Kingdom workshops, arsenical copper fragments, stone pounders, tool marks, quarry cuts, and chemical pollution in ancient sediments all show that Egyptian engineering was material, practical, and deeply physical. These tools were not supernatural, they were not invincible, they wore down, they broke, they had to be sharpened and remade. Their limits were part of the process. Yet when placed inside a larger system of trained labour, seasonal transport, scribal administration, and inherited craft knowledge, small tools became capable of large consequences. The pyramids do not demand impossible instruments. They demand an explanation for how ordinary instruments were coordinated with extraordinary persistence. That is the harder answer, and perhaps the more respectful one. It is easy to imagine a lost machine because a lost machine asks very little of us. It allows the pyramid to remain distant from human experience, but the evidence points toward hands, teams, roots, mud, rope, copper, stone, water, and time. It points toward quarrymen reading cracks in limestone, sailors watching river levels, metalworkers repairing dull edges, surveyors checking alignments, scribes recording deliveries, and builders adapting plans as stone rose around them. What survives in the record suggests not a single forbidden technology, but a civilization that turned many modest techniques into one overwhelming achievement. The true hidden machine was the coordination of the Nile state itself. Still, mystery remains because coordination does not explain every feature in detail. The subterranean chamber of the Great Pyramid remains rough and unresolved. The north face corridor is confirmed, but its purpose is still debated. The larger internal void is real as a detected anomaly, but its exact form and function remain uncertain. The air-filled spaces behind Menkar's eastern face may suggest a hidden entrance, but further evidence is needed. Buried features in the western cemetery and Saqqara may represent tombs, shafts, walls, or other structures not yet understood. The evidence remains incomplete, and that incompleteness is not a weakness of archaeology. It is the condition under which archaeology works. Ancient stone gives clues slowly, and sometimes it gives only the outline of a question. The pyramids themselves encourage this uncertainty because they were designed around controlled access. Some spaces were made to be sealed, some were made for construction and then hidden by success. Some may have been made to relieve pressure, not to carry meaning visible to human eyes. Others may have had ritual meanings that no inscription preserved. This creates a strange modern problem. A chamber that was never meant to be entered again can survive, but the reason for its closure may not. A relieving space can protect a burial chamber for millennia, yet leave later observers wondering whether it has a deeper symbolic role. A passage can be both practical and sacred. The old Egyptian habit of joining engineering to cosmic meaning means that modern categories are often too narrow. Structure and ritual may not be rivals. They may be the same decision seen from two different distances. The landscape holds the same ambiguity. The dried Nile branches near the pyramid fields show that transport was easier to imagine in the Old Kingdom than it appears from the modern desert. The harbour zones and sediment cores show activity that the bare plateau no longer displays. The causeways and valley temples connect the river world to the desert world, but they also connect logistics to ceremony. The Sphinx shows that bedrock could become monument, quarry, symbol, and risk all at once. Around the pyramids, the cemeteries show how royal power drew other lives and afterlives into its orbit. Giza was not an isolated construction site. It was a royal ecosystem in stone, water, labour, and memory. Modern science has not diminished that ecosystem. It has made it stranger in a more precise way. Moons from the sky reveal hidden density changes. Radar and resistivity find subsurface shapes. Ultrasound refines the image of spaces no one can safely enter. Vibration measurements show the monument as a responding body, not a dead mass. Sediment chemistry reveals copper activity where no tool remains in the hand. Environmental reconstruction restores waterways that disappeared from sight. Each method adds a layer, and each layer complicates the old image of a pyramid as a simple tomb. The monuments are tombs, but they are also foundations, machines of ritual, logistics hubs, astronomical gestures, political statements, geological interventions, and long-term experiments in stone endurance. This is why unsupported claims of hidden cities or impossible technologies are unnecessary. They are dramatic, but they flatten the real drama. The confirmed evidence is already full of buried architecture, unseen spaces, unfinished designs, and unanswered questions. The actual ancient Egyptians are more interesting than the imagined ones. They did not need to break the laws of nature. They needed to understand them well enough through practice to make stone last beyond dynasties. They needed to build in a world where the river shifted, tools wore out, chambers cracked, kings died, thieves waited, and religious meaning demanded permanence. They did not solve every problem perfectly. They solved enough of them for the pyramids to remain. And perhaps that is the most powerful part of the unfinished mystery beneath the pyramids. It is unfinished not because Egypt failed, but because survival is selective. The pyramid preserves mass better than method. It preserves royal names better than worker voices. It preserves chambers better than ropes. It preserves stone better than wood. It preserves the result better than the working day. The monument stands, but the process has to be reconstructed from fragments of papyrus here. A quarry mark there, a copper stain in mud, an unfinished room below ground, a void detected by particles from space. The builders left enough to prove their genius, but not enough to make that genius easy. So the story ends its main path where it began. Beneath the visible monument, the pyramids rise because the ground was chosen, cut, trusted, and transformed. They endure because pressure was managed, water was used, labor was organized, and stone was made to carry meaning as well as weight. Their hidden spaces remain powerful because they are neither empty fantasy nor fully explained engineering. They are the surviving gaps inside a real achievement. Egypt left its tools behind, but scattered them across scales in copper, in sediment, in voids, in corridors, in vanished rivers, in bedrock, and in the silence of rooms that still do not answer. The forbidden engineering under the pyramids is not forbidden because it was beyond humanity. It feels forbidden because it shows how much humanity once knew, how much it did not write down, and how much can still be lost beneath the stones that survive. Long after the last tool is set down, stone keeps its own kind of memory. It does not remember as people do. It does not hold a face, a voice, a tired hand, or the name of the worker who leaned into a rope beneath the sun. It remembers through pressure, through cuts, through chambers left dark, through scratches that escaped polishing, through copper traces settled into old harbour mud, through a corridor hidden behind blocks where no ordinary visitor was meant to pass. The pyramids survive as monuments of certainty, but the closer one listens to them, the more they become monuments of partial memory. They show what human beings can do, and they hide how much of doing is always lost. Perhaps that is why they remain so difficult to leave behind. They are not mysteries because nothing is known. Much is known now. The builders were human. Their tools were real. Their stone came from quarries. Their cargo moved by river. Their work followed plans, seasons, measurements, and command. The Nile carried material toward the desert edge. The plateau carried weight. The chambers carried belief. The hidden spaces carried stress, secrecy, or meanings now beyond easy recovery. And yet knowing this does not make the pyramids smaller. It makes them more haunting, because the answer is not a miracle descending from outside history. It is history itself, organized with a patience that feels almost unreachable from the present. Beneath the pyramids, the darkness is not empty. It is filled with choices. Some were practical, some sacred, some cautious, some ambitious, and some perhaps changed before they were complete. A rough chamber below Khufu's pyramid still keeps its unfinished silence. A hidden corridor still waits inside the north face. Ancient waterways lie dry under modern ground. The copper has faded from the tools, but not entirely from the earth. The people are gone, but the system they made remains. Not whole, not fully legible, but still standing against the weather of millennia. In the end, the pyramids do not give back everything that was placed into them. They were never designed to do that. They were designed to endure, to conceal, to transform a king's death into an architecture of permanence. But time has transformed them again. They now belong not only to kings, but to everyone who wonders how fragile lives can build something so durable, and how even durable things can carry loss inside them. The sun lowers over the plateau, the stone cools, the passages darken, and beneath the great shapes of Egypt, the old engineering rests quietly, still holding its weight, still keeping part of its secret.